What if I told you that we could have had cities in orbit around Earth by now? Or that human beings might have walked on Mars decades ago? There's an alternate timeline of space exploration. One where massive nuclear-powered rockets journeyed to the outer planets, where moon bases stood as monuments to human ambition, and where interstellar probes sailed on winds of starlight. These weren't just science fiction fantasies. They were real projects designed by some of the greatest scientific minds of the 20th century. Yet, for one reason or another, they never left the drawing board. They were simply too advanced for their time. Welcome to a journey through the forgotten archives of space history, a tour of 30 unrealized space projects that could have reshaped our future. In the heat of the Cold War, with the space race in full swing, engineers and visionaries on both sides of the Iron Curtain dreamed bigger than we often remember. They drew up plans for colossal vehicles and revolutionary missions that pushed the very limits of physics, engineering, and imagination. But time and again, these breathtaking ideas ran into the hard realities of politics, shifting budgets, public fear, and technological barriers just too high to clear at that moment in history. Each of these stories is more than a tale of what went wrong. It's a glimpse into a future that might have been, a future we're still chasing today. In this video, we'll explore everything from giant rockets that could have carried entire space stations in a single launch, to secret Soviet plans for Mars missions, to theoretical starships designed to cross the void between suns. These are the projects that redefined possible, and their legacy continues to inspire the next generation of explorers. So settle in, open your mind, and join me as we uncover the incredible and often heartbreaking stories of the space age that never was. To truly grasp why so many of these breathtaking projects remained confined to paper, we have to step back into the world that created them. The mid-20th century was a pressure cooker of ideology and innovation, a period where the Cold War transformed from a political standoff into an all-out technological sprint for supremacy. This wasn't just a competition, it was a high-stakes demonstration of national prowess, where every launch and every milestone was a powerful message broadcast to the entire world. The Soviet Union's successful Sputnik mission in 1957 didn't just orbit a small beeping satellite. It sent a shockwave through the American public and government, igniting a fierce determination to not just catch up, but to utterly surpass their rivals. This atmosphere of intense rivalry became the primary engine for space exploration, fueling a golden age of wildly ambitious thinking. With the prestige of nations on the line, money and resources flowed into aerospace and defense agencies, empowering engineers and scientists to dream on an unprecedented scale. The goal was no longer just to get an object into orbit or a person into space. It was to dominate the final frontier. This led to concepts that were staggering in their scope: colossal rockets, permanent orbital fortresses, and interplanetary missions that read like science fiction. The imagination of the era was virtually unbounded because the political will to achieve the impossible seemed for a time to be equally limitless. Design teams were encouraged to push the very edges of physics and material science, asking not, "Is this feasible?" but "How could we make this possible?" Yet, this very environment of breakneck competition also sowed the seeds for these projects' eventual cancellation. The relentless pace and shifting strategies of the Cold War meant that national priorities could change in an instant. A new administration would take office, a geopolitical event would redirect funding, or a competing military need would emerge. instantly deflating the momentum behind a multi-year billion-dollar program. The immense financial cost of these ventures was another constant hurdle. While the initial blank check mentality opened doors, the practical reality of funding such astronomically expensive projects often led to brutal triage. Even the most brilliantly designed spacecraft could be shelved overnight by a congressional budget committee looking for cuts. Furthermore, the technological leaps required were often simply too great for the era. Engineers were designing systems that demanded materials, computing power, and manufacturing techniques that wouldn't be invented for another 30 or 40 years. They were solving theoretical problems with slide rules and drafting tables, performing calculations that today would be handled in seconds by a laptop. This gap between visionary design and practical execution was a chasm that many projects could not cross in time to maintain political and financial support. What we are left with is a fascinating archive of alternate histories, a collection of detailed blueprints, wind tunnel models, and half-built prototypes that stand as monuments to a unique moment in time, when humanity dared to dream its biggest dreams under the shadow of mutual annihilation. Imagine a spacecraft not powered by the controlled burn of chemical fuels, but by the raw, earth-shattering force of nuclear bombs. This was the radical, almost unbelievable premise of Project Orion. In the late 1950s, at the height of the Cold War, a team of the world's brightest physicists, including the legendary Freeman Dyson, proposed a vehicle that would ride a continuous series of atomic explosions into the depths of our solar system and beyond. The design was shockingly straightforward in concept. The ship would eject a small nuclear device out the back, detonate it, and a giant, armored pusher plate would absorb the blast's force, transferring that immense energy into forward momentum through a system of massive shock absorbers. Then it would do it again and again, a pulse every few seconds, creating a thunderous, rhythmic push that would accelerate the vessel to speeds previously thought impossible. This wasn't just a paper concept. The team built and flew small-scale models using conventional explosives, proving the pulse propulsion principle worked. The numbers they calculated were staggering. A full-sized Orion could be as large as a city block, a veritable flying mountain capable of carrying thousands of tons of payload, entire space stations, large crews, and everything needed for long-duration voyages. Their mission plans read like something from a far future century. A journey to Saturn and its moons would take just 7 years. A flyby of Pluto was on the table. Perhaps most astonishingly, they envisioned an interstellar version that could reach Alpha Centauri within a human lifetime, using millions of nuclear charges to achieve a significant fraction of the speed of light. For a brief, brilliant moment, it seemed humanity had a shortcut to the stars. Yet, this incredible power was also its ultimate downfall. The same atomic energy that promised to unlock the solar system was the subject of intense global fear and burgeoning arms control treaties. The prospect of lofting hundreds of nuclear warheads into orbit and detonating them, even for peaceful purposes, was a political and public relations nightmare. The Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in the atmosphere and outer space, effectively pulled the plug on Orion's development. The team had to face a sobering reality. They had solved the physics, but they couldn't solve the politics or the profound ethical unease of turning weapons of mass destruction into tools of exploration. Project Orion remains a powerful symbol of a road not taken, a testament to an era when scientists dared to think with breathtaking audacity, only to be reminded that technological progress is inextricably linked to the society it emerges from. While American engineers were dreaming of riding atomic blasts to the stars, their Soviet counterparts were crafting a daring plan to conquer the next planet in line, Mars. In the shadows of the early 1960s, a secret Soviet design bureau began work on the TMK, the heavy interplanetary spacecraft. This was not a simple orbital capsule. It was a vessel designed for an epic, 3-year voyage to the Red Planet and back. The most ingenious part of the mission profile was its use of celestial mechanics. Instead of a direct flight, the TMK would use a gravitational slingshot around Venus to bend its trajectory toward Mars, a complex maneuver that would save enormous amounts of fuel but require pinpoint navigation over hundreds of millions of miles. The spacecraft itself was a marvel of cramped efficiency, a cylindrical habitat crammed with everything a small crew would need to survive the immense void between planets. Engineers had to solve problems no one had ever faced before. How do you shield humans from years of relentless cosmic radiation, far beyond the protective bubble of Earth's magnetosphere? How do you provide enough food, water, and air for a journey measured in years, not days? They envisioned closed-loop life support systems that would recycle everything, and even studied the psychological effects of long-term isolation in a tiny, windowless metal tube, a testament to their thorough, if grim, preparation. The cosmonauts would not land on Mars. They would simply fly by, becoming the first humans to lay eyes on another world from space, a fleeting glimpse before the long, lonely journey home. For a time, it seemed entirely possible. The Soviet space program was riding a wave of successes, having launched the first satellite, the first animal, and the first human into space. The momentum and the political will to beat the Americans to yet another monumental milestone was palpable. Detailed designs were drawn up, and prototypes of various systems were tested. Yet, the sheer audacity of the mission eventually collided with cold, hard reality. The risks were astronomically high. A single system's failure, a calculation error in the slingshot maneuver, or an unforeseen solar flare could doom the crew with no hope of rescue, stranding them in the infinite dark. The cost of developing such a specialized, one-shot spacecraft was also becoming prohibitive, especially as the moon race began to consume more and more resources and attention. Ultimately, the shifting sands of geopolitics sealed the TMK's fate. As the United States publicly committed to landing a man on the moon with the Apollo program, the Soviet leadership felt compelled to redirect all its efforts to winning that more visible, prestigious race. The secret Mars mission, for all its brilliance, was deemed a distraction. It was quietly shelved, its blueprints filed away, another ghost of a future that never came to pass. The TMK story is a powerful lesson in how a nation's technological ambitions can be abruptly rerouted by the pressures of international competition, leaving behind a legacy of what might have been a trio of Soviet cosmonauts, forever frozen in time on their planned trajectory to another world. If the colossal ambition of Project Orion was defined by its terrifying power, then the Sea Dragon rocket was defined by something else entirely, its breathtaking, almost brutal simplicity. Conceived in 1962 by the brilliant and unconventional aerospace engineer Robert Truax, the Sea Dragon was designed to be the ultimate heavy lifter, a rocket so enormous it would make every other launch vehicle look like a toy. Its payload capacity was set at an almost incomprehensible 550 metric tons to low Earth orbit. To put that in perspective, that's more than the entire weight of the International Space Station, launched in a single go. It's more than 5 times the capacity of today's most powerful rocket, the SpaceX Starship. The Sea Dragon wasn't just big, it was in a category of its own, a true leviathan of the space age. The genius of Truax's design lay in its rejection of complexity. While other rockets were becoming intricate networks of tiny, high-performance turbopumps and delicate plumbing, the Sea Dragon went in the opposite direction. Its engine was a masterpiece of simplicity, a massive, pressure-fed beast. Imagine a giant balloon. Instead of using complex machinery to force fuel into the engine, you would simply use pressurized gas from a tank to push the propellants into the combustion chamber. This approach eliminated thousands of moving parts, making the engine cheaper to build and far more reliable. But to make this work, the entire rocket had to be enormous, over 400 feet tall and 75 feet in diameter. It was so vast that the internal pressure of the fuel tanks alone was enough to provide structural rigidity, like a giant aluminum soda can. Its launch profile was just as audacious as its design. The Sea Dragon would never see a launch pad. Instead, it would be built in a shipyard, towed horizontally out to sea, and then upended and ballasted to float vertically in the ocean. It would launch right from the water, its engine bell submerged, using the ocean itself as a massive, sound-dampening launch platform. This eliminated the need for monstrously expensive launch facilities and meant the rocket could be launched from anywhere on Earth, directly into any required orbit. The entire philosophy was to make spaceflight cheap through sheer, overwhelming scale and simplicity, turning the launch of massive space stations and interplanetary arcs into a routine, industrial operation. For a time, the concept was taken very seriously. The company Ramjet invested in detailed studies and engineering analyses. The numbers were compelling, suggesting the Sea Dragon could launch payloads for a mere $60 per kilogram, a cost that even modern reusable rockets are still striving to achieve. But in the end, the very thing that made it brilliant also made it untenable: its unprecedented scale. The technological leap was simply too great. No one had ever fabricated rocket stages that large. The metallurgy, the welding techniques, the logistics of building and moving such a monster, it was all uncharted territory. The risks were perceived as immense. What if the pressure-fed engine concept encountered unforeseen instability in such a massive size? The idea of a catastrophic failure of a vehicle holding several thousand tons of propellant was too horrifying to contemplate. Ultimately, the political and budgetary winds shifted. As the Apollo program raced toward the moon, NASA's focus narrowed. The future, it was decided, belonged not to disposable super-heavy giants, but to a new, reusable spacecraft, the Space Shuttle. The Sea Dragon, for all its visionary promise, was deemed a bridge too far. It was quietly shelved, its blueprints becoming a fascinating footnote in history. Yet its spirit never truly died. The Sea Dragon's philosophy of achieving low cost through revolutionary scale and operational simplicity is the very same philosophy that drives private companies like SpaceX today. In a very real way, the ghost of that 1960s sea-launched behemoth is still whispering, urging us to think bigger, simpler, and bolder. While the Sea Dragon represented a philosophy of brute force and simplicity, another project brewing in the same era took a completely opposite approach, aiming for elegance, precision, and reusability. This was the X-20 Dyna-Soar, a name blending the concepts of dynamic flight and soaring. Envisioned by the US Air Force, this wasn't meant to be a capsule that splashed down into the ocean. It was a sleek, winged spacecraft designed to launch on a rocket, perform its mission in orbit, and then glide back to Earth, landing on a runway just like an airplane. In many ways, it was the true spiritual predecessor to the Space Shuttle, a concept decades ahead of its time that promised to revolutionize our access to space. The design specs for the Dyna-Soar were nothing short of revolutionary. It called for a single pilot to sit in a cockpit with a huge windshield, offering an unparalleled view of Earth and space, a stark contrast to the tiny, confined portholes of the Mercury capsules. Its airframe was to be constructed from radical new superalloys like Rene 41 and molybdenum, metals capable of withstanding the searing heat of re-entry, not through ablative burning like other spacecraft, but through heat absorption and radiation. This meant the same vehicle could be turned around and flown again and again and again. The military saw immense potential in this reusable platform, envisioning roles that sound like they're pulled from a spy thriller. It could be a high-speed reconnaissance vehicle, skimming the edge of space to peer over hostile territories. It could serve as an orbital bomber, a rapid response interceptor to destroy enemy satellites, or a crew transport to a secret space station. Development moved forward with serious momentum. Boeing won the contract to build the airframe, and a team of elite pilots, including a young Neil Armstrong, was selected to train for its flights. Full-scale mock-ups were built, and wind tunnel tests confirmed its aerodynamic stability. The plan was to launch the craft atop a modified Titan I rocket, with initial suborbital hops planned for 1965, building up to full orbital missions. The future of space travel seemed to be a pilot landing on a runway, not an astronaut bobbing in the ocean. But this very vision of the future became its greatest liability, as it placed the Dyna-Soar squarely in the middle of a growing bureaucratic battle. The fundamental problem was one of overlapping missions and muddled priorities. As the Dyna-Soar program advanced, NASA's Gemini program was also gaining steam. Gemini was designed explicitly as a two-person capsule to bridge the gap between Mercury and Apollo, focusing on crucial skills like spacewalking and orbital rendezvous. To the officials holding the purse strings in Washington, D.C., having two separate, incredibly expensive manned spaceflight programs seemed like a redundant waste of resources. The Air Force struggled to definitively prove the unique military necessity of the Dyna-Soar, especially when its proposed missions, like bombing and reconnaissance, were already being handled by increasingly sophisticated unmanned satellites and ICBM. The final nail in the coffin was the sheer cost. The Dyna-Soar was a complex, cutting-edge engineering challenge, and its price tag was ballooning at a time when the national focus and budget was being overwhelmingly directed toward winning the moon race with Apollo. In December 1963, just months after President Kennedy's assassination, Defense Secretary Robert McNamara made the decision to cancel the Dyna-Soar. He famously questioned why the U.S. needed to spend billions on a manned satellite when automated systems could do the job. The program was terminated, its technology shelved, and its pilots reassigned. Yet the Dyna-Soar was far from a failure. Its research into hypersonic flight, high-temperature metals, and lifting body re-entry profiles provided invaluable data that would directly contribute to the development of the Space Shuttle years later. It stands as a powerful case study in how innovation can be stifled not by a lack of vision or technical ability, but by internal competition and a failure to clearly define a mission that no other vehicle could fulfill. It was a brilliant solution desperately searching for a problem that the existing military and political landscape couldn't quite articulate. Even as the Air Force was sketching its sleek spaceplane, an even more audacious military vision was taking shape within a different branch of the service. In the immediate aftermath of Sputnik, a sense of urgency gripped the entire U.S. defense establishment. The fear wasn't just of losing a symbolic race, it was the terrifying prospect of the Soviet Union claiming the ultimate high ground, the moon itself. What if they turned it into a military platform, a base from which they could observe every move on Earth with impunity, or even launch attacks? This chilling scenario led the U.S. Army in 1959 to produce a stunningly detailed report titled Project Horizon. Its objective was not merely to land a man on the moon, It was to establish a permanent, fortified U.S. Army garrison on its surface. The scale of Project Horizon was almost beyond belief, a logistical undertaking that dwarfed even the later Apollo program. The plan called for a crew of 12 soldiers to begin construction on the lunar surface, eventually expanding to a permanent base housing a rotating contingent of dozens. This wasn't just a few tents and a flag. The blueprints included interconnected pressurized habitats buried under lunar soil for protection from radiation and micrometeorites, nuclear reactors for power, and even a prototype particle beam weapon for defense. The soldiers, essentially astronaut combat engineers, would use modified bulldozers and construction equipment to build landing pads, roads, and defensive fortifications. Their primary mission to conduct constant surveillance of Earth and space, establishing a lunar-based battle command that would dominate the cislunar sphere. To achieve this, the Army planned to weaponize the nascent American space program. The entire operation would be supplied by a relentless convoy of rocket launches. Using a derivative of the Saturn rocket family, which was still in its early design phases at the time, Project Horizon envisioned 147 launches in the first year alone. These wouldn't just be carrying astronauts, they would be freighters hauling thousands of tons of prefabricated base modules, construction materials, food, water, and fuel. The report meticulously calculated the costs, the trajectories, and the construction schedules, presenting it all with the dry, pragmatic tone of a military field manual. It was a plan for the invasion and occupation of another world, drafted with the same operational seriousness as a plan to secure a beachhead in Normandy. Yet, for all its meticulous detail, Project Horizon was doomed from the start. The immense cost, estimated at $6 billion initially with massive ongoing expenses, was a staggering sum for the era. But the project's true Achilles heel was political. The very idea of militarizing the moon ran counter to a growing global sentiment. President Eisenhower and later President Kennedy were keenly aware that claiming the moon for peaceful exploration was a powerful propaganda tool in the battle for global hearts and minds. Turning it into an armed camp would be a public relations disaster, validating Soviet claims of American imperialist ambitions and potentially triggering a new, even more dangerous arms race in space. Furthermore, the newly created NASA was aggressively asserting its role as the sole civilian agency for space exploration. The Army's plan was seen as a direct threat to NASA's authority and its peaceful scientific mandate. In the end, Project Horizon was quietly shelved, its voluminous reports relegated to the archives. It stands as one of the most stark examples of the tension between military strategy and peaceful exploration. It was a vision born from Cold War paranoia, a plan so thoroughly militarized that it failed to account for the profound symbolic power of the moon in the human imagination. While the Army was drawing up plans for lunar fortifications, NASA was inspiring the world with dreams of discovery and scientific achievement. Project Horizon serves as a fascinating and somewhat unsettling alternate history, a reminder that the path we took to the moon, for all its own political motivations, was one of peaceful exploration, and that the road not taken would have led to a very different and far more ominous lunar landscape. Not to be outdone by American concepts like Project Horizon, the Soviet Union was brewing its own plans for a permanent foothold on the moon, codenamed Zvezda, which means star in Russian. This was not a crude military outpost but a sophisticated scientific base, envisioned as the ultimate expression of Soviet technological and ideological triumph. While the Americans dreamed of soldiers, the Soviets dreamed of scientists, cosmonauts who would live and work on the lunar surface for months at a time, conducting groundbreaking research in geology, astronomy, and space medicine. The Zvezda program was the logical, breathtaking next step after a successful landing, a plan to not just visit the moon, but to truly inhabit it. The designs that emerged from the secret Soviet design bureaus were remarkably advanced, showcasing a deep understanding of the challenges of long-duration extraterrestrial living. The base was to be constructed from a series of cylindrical modules delivered separately and connected on the surface to form a sprawling complex. These weren't simple cans, they were designed with crew comfort and safety as a top priority. Engineers planned for large, pressurized workshops, dedicated laboratories, and even communal living areas to combat the psychological strain of isolation. Unlike the American vision of buried habitats, the Soviet modules were to be covered in a thick layer of loose lunar soil, or regolith, for protection against radiation and the extreme temperature swings between the 2-week-long day and night. Power would be supplied by a compact nuclear reactor, and sophisticated closed-loop life support systems would recycle air and water, creating a self-sustaining environment far from Earth. The entire ambitious enterprise, however, hinged on a single, colossal piece of technology, the N-1 rocket. This was the Soviet answer to America's Saturn V, a giant in its own right, standing taller than its American counterpart and powered by a bewildering 30 engines on its first stage alone. The N-1 was the key that would unlock the door to the moon, the only vehicle powerful enough to loft the heavy Zvezda modules, supplies, and cosmonaut crews on their translunar journey. The plan was methodical. First, unmanned N-1 launches would deliver the base modules and a lunar rover to the proposed site. Then, subsequent missions would bring the construction crew, who would assemble the base using remote-controlled machinery. Finally, regular rotational missions would begin, shuttling scientists back and forth to a fully operational lunar research station. But the N-1 rocket became the tragic flaw in this grand vision, a masterpiece of ambition undone by a fatal lack of testing and development time. Rushed into production under intense political pressure to beat the Americans to the moon, the N-1 was plagued by problems. Its complex cluster of 31st stage engines created horrific hydrodynamic and acoustic issues that its designers never fully solved. The Soviet program, operating under a veil of secrecy, also lacked the extensive ground testing facilities that NASA used to perfect the Saturn V's F-1 engines. Between 1969 and 1972, the Soviet Union attempted 4 test launches of the N-1 rocket. All 4 ended in catastrophic failure, with the most dramatic explosion occurring just seconds after launch, creating one of the largest non-nuclear blasts in human history and scattering debris across the Kazakh steppe. Each fiery failure of the N-1 was a hammer blow to the Zvezda program. With the Americans already walking on the moon, the political urgency to continue funding such an expensive and publicly disastrous endeavor evaporated. The repeated technical setbacks, combined with crippling budget constraints and internal bureaucratic battles, sealed its fate. By the early 1970s, both the N-1 rocket and the Zvezda moon-based program were officially cancelled, their blueprints and half-built hardware relegated to storage warehouses or museums. Yet, the intellectual investment was far from wasted. The extensive work on long-duration life support, modular habitat design, and crew psychology for Zvezda did not disappear. It became the direct foundation for the Soviet Union's next great achievement in space, the Salyut series of space stations, and ultimately, the core modules of the Mir station. The dream of living on the moon was deferred, but the knowledge gained in pursuit of that dream taught the Soviets how to live in space, proving that even our most spectacular failures can lay the groundwork for future success. But the quest to understand the fundamental building blocks of the universe doesn't stop at the edge of our atmosphere. In the 1980s, a group of visionary physicists proposed a solution to the greatest limitation facing their field: gravity itself. Their radical idea was to launch a particle accelerator into the void of space, creating a superconducting supercollider that would operate in the pristine environment of microgravity. On Earth, the immense energy required to smash particles together at near light speed demands machines of staggering size and cost, their circular tunnels measured in miles, all to counteract the constant pull of gravity that strains their perfect alignment and limits the strength of their guiding magnetic fields. In the weightlessness of orbit, these constraints would vanish. A space-based collider could, in theory, achieve energy levels far beyond anything possible on our planet, potentially unlocking the secrets of dark matter, extra dimensions, and the very first moments after the Big Bang. The engineering behind such a concept was as breathtaking as the science it promised. Imagine the complexity of the International Space Station, but dedicated to a single, monumental machine. This orbital collider would require massive, perfectly calibrated superconducting magnets to be manufactured and assembled in space, a feat of robotic construction that we are only now beginning to approach. It would need a power supply rivaling that of a small city, likely drawn from vast arrays of solar panels, and a cooling system capable of maintaining its components at temperatures near absolute zero in the unforgiving thermal extremes of space. Every nut, bolt, and superconducting coil would have to be launched from Earth at astronomical cost, or perhaps mined and manufactured from asteroids in a future we have yet to realize. The concept was a beautiful marriage of particle physics and astronautics, but it demanded technologies that were little more than speculative dreams in the 1980s. Ultimately, the dream of a super collider in space collided with the hard realities of funding and terrestrial progress. The estimated price tag was so colossal, it made even the most ambitious Earth-based projects seem frugal by comparison. At the same time, the scientific community was rallying behind a new, ground-based project, the Large Hadron Collider in Europe. The LHC offered a more practical, albeit still enormously complex and expensive, path to new discoveries. With its promise of tangible results within a foreseeable time frame, the LHC captured the world's attention and funding, leading to the monumental discovery of the Higgs boson in 2012. The space-based collider, by contrast, was dismissed as a fanciful thought experiment, a project so far ahead of its time that it belonged to a future century of space industrialization. It remains a powerful symbol of an uncompromising ambition to push the boundaries of knowledge, regardless of the practical hurdles, reminding us that the next great leap in physics might not happen in a tunnel under Switzerland, but in the silent, gravity-free expanse between the stars. For all the audacious plans to reach other worlds, one of the most persistent and elegant solutions to a fundamental human problem has remained for decades just out of reach. We are creatures of gravity. Our bodies, from our cardiovascular system to our muscles and bones, have evolved over millions of years to function under the constant pull of Earth. Remove that pull, as we've learned from astronauts living on the International Space Station, and the human form begins to deteriorate in subtle and profound ways. Muscle mass wastes away, bones lose density at an alarming rate, and some astronauts even experience changes in their vision. These aren't minor inconveniences. They are significant barriers to the dream of humanity becoming a truly spacefaring species, capable of multi-year journeys to Mars and beyond. The solution to this problem was proposed not by a biologist but by a rocket scientist, and it was breathtakingly simple in its concept. If you can't bring gravity with you, you can create it yourself through motion. This was the genius behind the rotating space station, an idea most famously championed by Wernher von Braun in the 1950s. His vision, widely publicized in a series of Collier's magazine articles, captured the public imagination. It was a gigantic, wheel-shaped structure spinning slowly in the void. The centrifugal force generated by this rotation would push everything inside outward against the outer rim of the wheel, perfectly simulating the feeling of gravity. In this elegant environment, astronauts could live and work for years without suffering the physical decay of zero-G. They could walk on floors, pour a cup of coffee, and sleep in a normal bed, all while orbiting high above the Earth. This vision was so compelling that it became the definitive image of humanity's future in space, immortalized in Stanley Kubrick's masterpiece, 2001: A Space Odyssey. The film's stunning depiction of the rotating space station V, with its vast, graceful interior and Pan Am shuttles docking at its central hub, didn't feel like science fiction. It felt like a preview, a logical and inevitable next step. The station featured a Hilton hotel, restaurants, and comfortable seating areas, a home away from home, made possible by the gentle, artificial gravity created by its stately spin. For a generation, this was what space was supposed to look like. Yet here we are, decades later, living in a reality of zero-gravity tin cans. Why did von Braun's beautiful vision never materialize? The answer lies in the immense, daunting challenge of orbital construction. Building the International Space Station, a relatively modest collection of modules that does not spin, required over a decade and more than 30 assembly flights by the Space Shuttle. It was one of the most complex and expensive engineering projects in human history. Now, imagine the scale of a rotating wheel large enough to make the physics work properly. To avoid the disorienting Coriolis effect, which would make astronauts feel dizzy every time they turned their heads, the station would need to be enormous, perhaps a kilometer or more in diameter. The materials, the propulsion to spin it up, the perfectly balanced structure, and the thousands of hours of risky spacewalks needed to assemble it presented a set of engineering and financial hurdles that were simply too high to clear in the 20th century. Faced with these overwhelming challenges, space agencies made a pragmatic choice. They prioritized the science that could be done in microgravity over the comfort of long-term human habitation. The path forward became the ISS, a brilliant laboratory for studying the effects of zero gravity, not a prototype for overcoming it, but the dream of artificial gravity has never died. As we now set our sights on months-long journeys to Mars, the health problems of zero gravity are no longer a secondary concern. They are a primary mission risk. Today, engineers are revisiting von Braun's old blueprints with fresh eyes. New concepts for creating artificial gravity are being studied, from smaller, tethered spacecraft that spin around a common center of mass to ambitious new designs for Mars transfer vehicles that include a rotating crew section. The old idea, once deemed too complex for its time, is finding new life, proving that in the long arc of space exploration, a brilliant concept is never truly abandoned. It just waits for the right moment to spin up once again. What if you could travel to the stars without a single drop of fuel in your tank? This was the astonishing promise of the Bussard Ramjet, a theoretical starship concept that sounds more like science fiction than hard physics. Proposed in 1960 by physicist Robert W. Bussard, the idea was deceptively simple and utterly brilliant. Instead of hauling all the propellant for a journey spanning light years, an impossible weight for any rocket, this craft would become a celestial fisherman, casting a net into the void to catch its fuel along the way. It would use an enormous electromagnetic field, spanning thousands of kilometers in diameter, as a kind of invisible scoop to gather the thin mist of hydrogen atoms that drift through interstellar space. This collected hydrogen would then be funneled into a compact fusion reactor, ignited into a star-like blaze and expelled out the back as a devastatingly powerful exhaust, accelerating the vessel to a significant fraction of the speed of light. The elegant beauty of this concept lies in its self-sufficiency. The faster the ship goes, the more hydrogen it rams into its magnetic scoop, which in turn provides more fuel for the fusion reactor, generating even greater thrust. It's a virtuous cycle of acceleration that could, in theory, continue almost indefinitely, pushing the craft closer and closer to the ultimate speed limit of the universe. The mathematics behind it was sound, painting a picture of a vehicle that could reach Proxima Centauri, our nearest stellar neighbor, in a matter of decades rather than millennia. For a moment, it seemed like humanity had been handed a blueprint for the galaxy, a way to overcome the tyrannical constraints of the rocket equation that had grounded all previous concepts of interstellar travel. It captured the imagination of scientists and authors alike, becoming a staple in science fiction novels and forever linking Bussard's name with the dream of sailing the cosmic winds. But as with so many of these visionary ideas, the transition from the blackboard to the blackness of space revealed a host of brutal practicalities. The first and most formidable challenge was the sheer scale of the magnetic scoop. To generate a field large enough to collect a meaningful amount of hydrogen from the near-perfect vacuum of interstellar space, where there might be only 1 or 2 atoms per cubic centimeter, the electromagnet would need to be truly planetary in size. We are talking about a structure wider than the Earth, a feat of engineering that borders on the magical. Furthermore, maintaining and powering such a colossal magnetic field across billions of kilometers presents problems we have no current means of solving. The energy required would be astronomical, and the materials needed to generate the field simply don't exist within our known periodic table. Then there was the problem of the fuel itself. Later, more detailed calculations revealed a critical flaw in the initial assumption. Within our region of the galaxy, the interstellar medium is not composed purely of the hydrogen atoms the Ramjet needs for proton-proton fusion, the same reaction that powers our Sun. A significant portion is actually ionized hydrogen, protons that would be repelled by the craft's positively charged magnetic scoop instead of being gathered in. This meant the actual fuel collection rate might be far lower than originally hoped, starving the fusion reactor and stalling the entire beautiful concept. Additional issues, like the incredible drag force created by ramming into even a sparse medium at relativistic speeds, and the lethal radiation generated by the fusion process, added further layers of seemingly insurmountable complexity. The Bussard Ramjet, therefore, stands as a perfect monument to a specific kind of genius theoretical brilliance, leaping decades ahead of practical capability. It is a concept that is fundamentally correct in its physics, yet hopelessly beyond our engineering grasp, a paradox that defines so many of these unrealized projects. It was an idea born from a moment of incredible optimism, when the new tools of nuclear physics and relativity seemed to offer keys to every locked door in the universe. While we may never see a functioning Bussard Ramjet, its legacy is secure. It expanded our thinking about what might be possible, forcing scientists to grapple with the real-world problems of interstellar travel and inspiring generations to look up at the stars not as distant points of light, but as destinations waiting for a technology mature enough to make the journey. While the Bussard Ramjet was a dream of peaceful interstellar exploration, the Cold War was simultaneously fueling a much darker and more immediate ambition in orbit. As the 1980s dawned, the final, most intense phase of the US-Soviet rivalry sparked a frantic effort to turn the heavens into a battlefield. The ultimate expression of this drive was not a mere satellite with a defensive capability, but a dedicated, massive warship designed for space, the Soviet Polyus spacecraft. This was not a scientific probe or a symbol of peaceful exploration. Polyus was conceived as a titan of orbital warfare, a direct and terrifying response to President Reagan's Strategic Defense Initiative, which the press had chillingly dubbed Star Wars. The specifications for Polyus were staggering, a testament to the sheer audacity of its design bureaus. It was to be the largest spacecraft ever launched by the Soviet Union, a behemoth over 120 feet long and weighing nearly 80 tons. Its primary mission was twofold, a combination of offensive and defensive capabilities that blurred the line between shield and sword. Its main weapon was a megawatt-level carbon dioxide laser, powerful enough to blind the delicate optical sensors of American early warning and reconnaissance satellites, effectively leaving the US military deaf and dumb in space. But its designers didn't stop there. Polyus was also equipped with a battery of small interceptor missiles, designed to physically destroy incoming ballistic missiles or enemy satellites. To complete its arsenal, it even had a rapid-fire cannon for close-range engagements, turning it into a veritable flying battleship intended to dominate the low Earth orbit battlefield. The development of such a complex weapon system was shrouded in absolute secrecy, known only by its codename, Skiff. The pressure to get it into orbit was immense, driven by a genuine fear in the Soviet military that the American SDI program would render their nuclear deterrent obsolete. This pressure, however, created a fatal rush. The Polyus module was designed to be launched on the very first flight of the enormous Energy rocket, the Soviet Union's new super-heavy lift vehicle, and a technological marvel in its own right. The launch in May 1987 was a moment of supreme tension and high stakes. The Energy rocket itself performed flawlessly, a roaring success that demonstrated incredible Soviet engineering prowess. It delivered its payload, the Polyus warship, perfectly into the intended initial orbit. The launch vehicle had done its job. The failure was entirely with the payload itself. In a cruel twist of irony for a weapon designed to rely on sophisticated software and targeting systems, Polyus was doomed by a single, catastrophic software error. The spacecraft's onboard computer was programmed to perform a specific maneuver after separation from the Energy rocket. It was to rotate itself 180 degrees and then fire its own engines to push itself into a higher, stable orbit. But the programmer had made a fundamental mistake in the code's logic. Instead of completing a half-turn, the computer commanded the spacecraft to keep rotating, executing a full 360-degree flip. This meant that when it fired its orbital insertion engines, it was pointing back toward Earth. Instead of soaring higher, the massive billion-ruble battle station fired itself directly into the thicker layers of the atmosphere, where it burned up and disintegrated over the Pacific Ocean. It was a stunning, almost unbelievable end for a project of such immense strategic importance, a multi-year effort vaporized in minutes by a single line of incorrect code. The humiliating failure was a devastating blow from which the Polyus program never recovered, but its ultimate cancellation came from a force even more powerful than a software glitch: the shifting winds of global politics. By the late 1980s, the intense friction of the Cold War was beginning to ease. The new Soviet leadership under Mikhail Gorbachev was pursuing policies of glasnost and perestroika, seeking warmer relations with the West and embarking on significant nuclear disarmament talks. In this new atmosphere of thawing tensions, pouring billions of rubles into a massive, provocative orbital weapons platform began to seem not just wasteful, but dangerously counterproductive. The project was quietly shelved, its technology repurposed or abandoned. The Polyus story serves as a stark, dual-layer cautionary tale. It is a classic lesson in how frantic rushing and inadequate testing can doom even the most advanced technological project. But on a much larger scale, it is a powerful reminder of how swiftly geopolitical realities can change, rendering a once vital strategic imperative suddenly obsolete and unwanted. It stands as a ghostly sentinel in space history, a warning of a militarized future we narrowly avoided, and a testament to the fact that sometimes the greatest threat to an advanced weapon is not another weapon, but the sudden arrival of peace. Just as the Cold War era was defined by projects of staggering scale and cost, the post-Apollo landscape of space exploration began to grapple with a new and persistent challenge: the relentless pressure of budgets. The dream of reaching Mars, however, never faded. It simply had to become smarter, leaner, and more ingenious. In the early 1990s, at a time when NASA's own Mars plans involved colossal orbiting space stations and flotillas of spacecraft, a brilliant and fiercely determined aerospace engineer named Robert Zubrin offered a radical alternative. He called it Mars Direct, and its core philosophy was a powerful rejection of overcomplexity. Why build a massive interplanetary ark in Earth orbit, hauling every drop of fuel and breath of air from our planet, when Mars itself could provide the resources needed for the journey? This concept, known as in-situ resource utilization, wasn't just a minor tweak. It was a complete reimagining of how to explore another world, turning a desolate planet into a gas station for humanity. The elegance of Mars Direct lay in its beautiful two-act mission architecture. The first spacecraft to launch wouldn't carry humans at all. It would be an unmanned Earth return vehicle, sent on a direct trajectory to the Red Planet. On board would be a small, automated chemical processing plant and a supply of hydrogen. Upon landing, this robotic pioneer would get to work. It would suck in the thin Martian atmosphere, which is 96% carbon dioxide, and combine it with the imported hydrogen in a simple chemical reaction called the Sabatier process. The output, methane and oxygen, the fundamental components of rocket fuel. It would also extract and store water from the Martian soil. Over the course of nearly a year, this little factory would patiently manufacture and stockpile all the propellant needed for the crew's journey back to Earth. By the time the astronauts arrived, their ride home would be waiting for them, fully fueled and ready, having literally made its gas from thin air. This single innovation changed everything. By not having to carry the return fuel from Earth, the entire mission mass was slashed by an enormous margin. The crew could launch in a much smaller, simpler habitation module, landing it directly on Mars next to their pre-prepared return vehicle. Their home on the Red Planet would be the same module they flew in on, and their rover would be powered by methane produced from the atmosphere. The plan was audacious yet profoundly simple, cutting out the need for expensive and risky orbital assembly around Earth or Mars. Zubrin and his colleagues at the Mars Society advocated for it with missionary zeal, arguing that it was not only feasible with existing technology, but that it could be achieved for a fraction of the cost of NASA's own bloated proposals, perhaps as little as $30 billion. They presented it as the Apollo program for a new generation, a direct, focused, and affordable path to putting boots on Martian soil within a decade. Despite its compelling logic and a growing chorus of support from within the scientific community, Mars Direct ran headlong into the immovable object of institutional tradition. NASA's long-standing vision for Mars, influenced by the legacy of the space station program, was built around a different philosophy, one of orbital infrastructure, multiple vehicle types, and a cautious, step-by-step approach that involved building a gateway station near the Moon first. This bureaucratic momentum, combined with concerns about the perceived risks of relying on unproven ISRO technology on another planet, meant that the agency's official plans continued to favor more complex and exponentially more expensive architectures. Funding for a bold, focused Mars mission also never materialized from Congress as political priorities shifted over the years. Mars Direct, for all its brilliance, remained a paper project, a set of beautifully reasoned PowerPoint slides and a book titled The Case for Mars. Yet, to call Mars Direct a failure would be to profoundly misunderstand its impact. While NASA continued on its own path, the core ideas of Zubrin's plan were quietly adopted and championed by a new player in the space arena, the private sector. Elon Musk has repeatedly and publicly cited Mars Direct as a key inspiration for the development of SpaceX's Starship vehicle. The entire Starship concept is built upon the very same principle of in-situ resource utilization that Zubrin championed decades ago. Starship is designed to land on Mars, refuel using propellant mined and manufactured from the Martian atmosphere and ice deposits, and then fly back to Earth. The torch of Mars Direct, though never lit at NASA, was passed to a generation of engineers and entrepreneurs who saw its elegant logic not as a risk, but as the only sane way to become an interplanetary species. It stands as a powerful testament to how a truly innovative idea can be stifled by institutional inertia in the short term, only to resurface later and fundamentally change the trajectory of exploration. While giants like the United States and the Soviet Union were locked in a superpower struggle for the heavens, a quieter, more modest space program was taking shape off the coast of Great Britain. The Black Arrow rocket was a testament to a different kind of ambition, not one of overwhelming scale or military dominance, but of national self-reliance and elegant, economical engineering. In an era defined by the colossal Saturn V and the secretive N1, the Black Arrow was a pint-sized pioneer, standing a mere 13 meters tall. It was designed with a very specific, pragmatic purpose: to give the United Kingdom its own independent, sovereign means of reaching orbit, freeing it from the need to rely on either American or Soviet launch services to put its satellites into space. It represented a nation's determined effort to secure its own seat at the table in the new space age, not as a guest but as a player in its own right. The development of Black Arrow was a masterclass in doing more with less. Where other rockets were monuments to immense government budgets, this was a project built on frugality and clever design. It used a propulsion technology that was robust and well understood, a kerosene and high-test peroxide engine, a choice that prioritized reliability and lower cost over cutting-edge performance. Its launch strategy was equally pragmatic. Instead of building an expensive, permanent launch complex, the British team chose a remote and windswept location, Woomera in the Australian outback. The entire launch operation was remarkably lean, a far cry from the vast armies of technicians controlling Apollo launches from Cape Canaveral. For Britain, Black Arrow was never about winning a race. It was about proving a point that a nation could develop and operate its own complete space launch system, from design to deployment on a sensible budget. And prove it they did. After 3 developmental flights that honed the vehicle's design, the 4th and final Black Arrow rocket, designated R3, stood on the launch pad in October 1971. Its payload was a small, 72-kilogram satellite named Prospero, after the sorcerer from Shakespeare's The Tempest who commands the forces of nature. In a beautiful piece of symbolism, the satellite itself was a technological charm, carrying experiments to measure the micrometeorite density and radiation environment in orbit. The launch was a flawless success. Prospero was gently released into a polar orbit, its signals chirping back to Earth, and the United Kingdom officially joined an elite club of just 6 nations that had successfully launched a satellite on their own indigenous rocket. It was a moment of immense national pride and a stunning validation of the entire Black Arrow program's philosophy of modest, incremental, and successful engineering. Yet, in a cruel and almost unbelievable twist of bureaucratic fate, this triumph was already a posthumous victory. Unbeknownst to many of the engineers and technicians celebrating at Woomera, the British government had already decided to cancel the Black Arrow program months before that final, successful launch. In a move driven entirely by short-term budget cuts, the government had deemed the project too expensive to continue, calculating that it would be cheaper to simply hitch rides on American rockets for future satellite needs. The news that the cancellation had been confirmed before the launch, but kept secret to avoid demoralizing the team, added a layer of profound tragedy to the achievement. The very rocket that had just secured Britain's place in space was immediately retired, its technology shelved, and its launch team disbanded. In a single, bewildering act, the United Kingdom became the first and only country in history to successfully develop a satellite launch capability and then voluntarily abandon it immediately afterward. The legacy of Black Arrow is not one of technological failure, but of a profound strategic miscalculation. The government's decision was a classic example of prioritizing immediate fiscal savings over long-term technological sovereignty. By giving up its independent access to space, the UK placed its entire national space strategy at the mercy of foreign powers and the fluctuating prices and priorities of the international launch market. For decades, British satellites, including those for crucial national defense and communications, had to wait in line and pay a premium for slots on American or European rockets. The lesson of Black Arrow is a cautionary tale that resonates deeply today, as numerous other nations now scramble to develop their own launch capabilities, having seen the strategic vulnerability that comes with dependence on others. It stands as a poignant reminder that true capability cannot be bought off a shelf. It must be built, nurtured, and maintained, even when the balance sheet suggests it might be cheaper to simply look the other way. But while the Black Arrow story was one of a capability gained and then surrendered, another British endeavour was looking far beyond Earth's orbit, aiming for a target so distant it required a complete reimagining of what a spacecraft could be. This was Project Daedalus, a volunteer-led study that stands as one of the most detailed and ambitious blueprints for interstellar travel ever conceived. In the 1970s, with government space agencies focused on the inner solar system, a group of scientists and engineers from the British Interplanetary Society took it upon themselves to answer a seemingly impossible question: how could we send a probe to another star within a human lifetime? Their answer was a colossal two-stage unmanned vessel designed to journey to Barnard's star, a red dwarf just under 6 light-years away. The sheer audacity of the project was breathtaking. This wasn't a modest proposal but a 5-year, fully funded study resulting in a multi-volume report that read like a real mission plan, complete with intricate engineering diagrams and precise trajectory calculations. The heart of Daedalus's revolutionary design was its propulsion system, a refined and controlled version of the explosive concept behind Project Orion. Daedalus would not use fission bombs. Instead, it would employ a far more powerful and efficient technology: nuclear pulse fusion. Imagine a delicate, autonomous factory hurtling through the void. Every few seconds, it would inject a tiny pellet of deuterium and helium-3 fuel derived from the atmosphere of Jupiter or the lunar soil into a massive combustion chamber. There, a powerful electron beam would compress and ignite the pellet, triggering a miniature thermonuclear explosion. The force of this micro-sun would be contained by a giant magnetic nozzle and directed out the back, pushing the spacecraft forward with incredible force. This process would repeat in a rapid, rhythmic pulse, tens of thousands of times, gradually accelerating the 4,000-ton vehicle to an almost unimaginable 12% of the speed of light. At that velocity, the probe would cover the vast distance to Barnard's star in just 50 years, a blink of an eye on the cosmic timescale. The mission profile was as complex as the engine itself. After a 4-year acceleration burn, the first stage would detach and fall away. The second stage would then fire for another nearly 2 years before finally coasting for the remainder of the decades-long cruise. As it approached its target, this robotic ambassador would not slow down. A flyby was the only feasible option, but it would be a profoundly productive one. The mothership would deploy a small armada of sub-probes and telescopes, casting them into the alien star system to perform a whirlwind reconnaissance. These sophisticated instruments would have mere hours to map planets, analyze atmospheres, and search for any signs of chemistry or activity that might hint at the presence of life, relaying every precious byte of data back to a waiting Earth before the entire assembly sped on into the eternal darkness of the interstellar deep. Project Daedalus was, of course, never built. The technological hurdles were, and still are, monumental. The helium-3 fuel would require mining operations on a scale we can scarcely envision. The engine's components would need to withstand unimaginable temperatures and forces, and the probe's autonomous systems would have to operate flawlessly for half a century without any possibility of repair. Yet to dismiss it as mere fantasy is to miss its profound importance. Daedalus was a thought experiment conducted with rigorous scientific discipline. It forced physicists and engineers to grapple with the real-world problems of interstellar travel, moving the concept from the realm of pure fiction into the domain of theoretical engineering. Its legacy is immense. It directly inspired a NASA counterpart, Project Icarus, and its spirit of using known physics to design a plausible starship underpins modern initiatives like Breakthrough Starshot, which aims to send gram-scale probes pushed by lasers. Most importantly, Project Daedalus stands as a towering monument to the power of pure, unfunded curiosity. It proved that a dedicated group of volunteers, working outside the bureaucratic constraints of national agencies, could produce a vision of the future more bold and inspiring than any government plan. It was a gift from one generation of dreamers to the next, a detailed map to the stars left on the table for when we are finally ready to make the journey. Meanwhile, as some looked to the stars for exploration, others envisioned a way to harness their very essence to solve an earthly crisis. The 1970s were a decade of profound energy anxiety, defined by oil embargoes, gas station lines, and a grim realization of the world's dependence on finite, politically volatile fossil fuels. In this atmosphere of scarcity, a brilliant and seemingly limitless alternative emerged from an unlikely place: the drawing boards of NASA and the US Department of Energy. The concept was known as the Solar Power Satellite, or SPS, and its promise was nothing short of revolutionary. Imagine a constellation of colossal structures, each weighing tens of thousands of tons, parked in a fixed position 22,000 miles above the Earth. In the perpetual, unfiltered sunlight of geostationary orbit, these platforms would be covered in vast arrays of photovoltaic cells, soaking up solar energy 24 hours a day, without any interruption from clouds, night, or atmospheric interference. They would generate power on a scale that dwarfed any terrestrial power plant, but the real genius was in how that power would get home. The proposed method for delivering this energy was a concept that seemed pulled from the pages of a science fiction novel: wireless power transmission. The satellites would convert the collected direct current electricity into microwaves, a form of electromagnetic radiation. These microwaves would then be focused into a precise, low-energy beam and transmitted down to a gigantic receiving antenna on Earth, known as a rectenna, which could be several miles in diameter. This rectenna, looking like a vast, sprawling chicken wire grid, would then convert the microwave energy back into electricity and feed it directly into the terrestrial power grid. The beam itself was designed to be perfectly safe, its intensity comparable to the microwave energy leaking from a conventional oven door, ensuring it would have no harmful effect on aircraft, birds, or any life that passed through it. The vision was one of absolute abundance, a base load, always-on source of clean energy that could power entire cities and finally wean civilization off its destructive addiction to coal, oil, and gas. The engineering designs for these satellites were as awe-inspiring as the concept itself. They were to be truly enormous structures measuring kilometers in length, making them the largest objects ever constructed by human hands. Building them would require a Herculean effort in orbital construction, a massive fleet of reusable space shuttles far more advanced than what was then on the drawing board, and a permanent workforce of astronauts living in space, functioning as assembly crews. The projected cost of the entire endeavor was appropriately astronomical, running into hundreds of billions of dollars even in 1970s money. Yet, for a brief, optimistic moment, the potential payoff seemed worth the immense investment. The promise of limitless, clean energy was a siren song too beautiful to ignore, and serious studies were commissioned, bringing together the best minds in aerospace, energy, and physics to hammer out the details. Ultimately, however, the sheer magnitude of the challenges brought the dream crashing back to Earth. The most formidable obstacle was the upfront cost and the mind-boggling complexity of the required space infrastructure. The world simply did not have the heavy lift rocket capacity, the autonomous robotics, or the in-orbit manufacturing techniques needed to even begin such a project. The energy transmission efficiency, while theoretically sound, was also a major concern. Any significant loss in the conversion from DC to microwave and back to electricity would erase the economic viability of the entire system. Furthermore, the project began to face growing public skepticism and concern. Though scientists insisted the microwave beam was harmless, the public image of a powerful energy beam shot from space was a public relations nightmare, easily caricatured by opponents as a potential weapon or an environmental hazard. Faced with these daunting technical, economic, and social hurdles, and with political winds shifting towards more immediate and terrestrial energy solutions, the solar power satellite concept was quietly filed away by the early 1980s, dismissed as a well-intentioned but hopelessly premature fantasy. But like so many of these advanced ideas, its time may finally be coming. The world today is gripped by a new, even more urgent energy crisis, the pressing need to decarbonize our economy to avert climate catastrophe. This renewed desperation has sparked a dramatic renaissance for the concept, now often referred to as space-based solar power. The technological landscape has also transformed in its favor. The cost of launching mass to orbit is plummeting thanks to reusable rockets from companies like SpaceX. Advances in robotics and in-orbit servicing now make the idea of autonomous assembly in space far more plausible. Perhaps most critically, the efficiency of the key components solar cells, wireless power transmission, and power beaming electronics has improved by orders of magnitude since the 1970s. New designs propose using vast, lightweight modular mirrors to concentrate sunlight onto smaller, highly efficient photovoltaic panels, drastically reducing the mass and cost of the satellites. What was once a prohibitively expensive dream is now being re-evaluated by space agencies from the US to Japan to Europe. and by several private companies as a potentially viable solution to the century's greatest challenge. The story of the solar power satellite is a powerful lesson in patience, demonstrating that an idea isn't always wrong. It's sometimes just waiting for the rest of the world to catch up. If the sleek, winged dream of the Dyna-Soar was the first attempt at a reusable spacecraft, and the space shuttle was its complex, compromised reality, then the X-33 VentureStar was meant to be the final, perfected evolution, a machine that would finally make spaceflight as routine and economical as air travel. Born in the mid-1990s, this wasn't just another government rocket program. It was a radical public-private partnership between NASA and Lockheed Martin, designed to leapfrog an entire generation of technology. The ambitious goal was nothing less than a 100-fold reduction in the cost of launching payloads to orbit, dropping the price from around $10,000 per pound to a mere $100. The vehicle designed to achieve this was a breathtakingly elegant, futuristic craft that looked like it had flown straight off a movie screen. The X-33 was conceived not as a full-scale orbital vehicle, but as a half-scale technology demonstrator, a proof of concept that would pave the way for its operational big brother, the VentureStar. Its design was a clean-sheet rejection of everything that made the space shuttle so expensive and labor-intensive to operate. Where the shuttle relied on expensive, disposable external fuel tanks and solid rocket boosters that had to be fished out of the ocean and painstakingly refurbished after every flight, the X-33 was a pure single-stage to-orbit vehicle. It would take off vertically like a rocket, reach orbit under its own power, and then glide back to Earth to land horizontally on a runway, ready to be refueled and fly again within days, not months. This rapid reusability was the absolute key to its economic promise, and every aspect of its design served that ultimate purpose. Two revolutionary technologies were at the heart of this bold vision. The first was its exotic linear aerospike engine. A conventional rocket engine has a bell-shaped nozzle carefully tuned to perform optimally at a specific altitude. The aerospike was a complete rethinking of that principle. It looked like a V-shaped wedge with rocket combustion occurring along its outer edges. Instead of a contained bell, it used the atmosphere itself as the other half of the nozzle. This ingenious design meant the engine was automatically efficient at all altitudes, from sea-level takeoff to the vacuum of space, eliminating the need for complex, heavy multi-stage engines. The second breakthrough was its airframe. To save every possible ounce of weight, the X-33 was to be built almost entirely out of lightweight composite materials, specifically graphite composite. This wasn't just using composites for small parts. This was building the entire primary structure, including the massive liquid hydrogen fuel tanks, out of this advanced, strong, and feather-light material. For a few years, the project surged forward with incredible momentum. A full-scale mock-up was built, and construction began on a massive new launch facility in Utah. The promise was intoxicating, and the future it painted was one of frequent, affordable access to space. But then, during a routine ground test in 1999, the dream hit a wall, literally. One of the revolutionary composite liquid hydrogen tanks, a critical piece of technology that was supposed to make the vehicle light enough to succeed, failed catastrophically during a pressure test. It ruptured, unable to handle the extreme cold and stresses of holding the super-chilled fuel. Fixing this fundamental flaw proved to be a nightmare. The composite materials, for all their promised lightness and strength, behaved unpredictably. They developed micro-cracks, and the bonds between layers proved unreliable under the intense cryogenic conditions. Every attempted solution added more weight, and in the brutal calculus of rocketry, added weight is a death sentence for a single stage-to-orbit vehicle. Each pound added to the structure is a pound subtracted from the payload, erasing the very economic advantage the vehicle was supposed to create. After spending over $1.3 billion, NASA and Lockheed Martin found themselves in an inescapable trap. The technical challenges with the composite tanks were proving too expensive and time-consuming to solve. The projected cost to complete the X-33 demonstrator had ballooned, and the timeline had stretched out for years. In 2001, with the project over budget and behind schedule, NASA made the difficult decision to pull the plug. The X-33 program was cancelled, and the nearly completed prototype was left to gather dust in a hangar. In the immediate sense, it was a staggering failure, yet its legacy is far more complex and ultimately positive. The X-33 served as a monumental billion-dollar lesson in the risks of pushing materials science too far, too fast. The data from its development, especially the painful lessons learned about the behavior of composites under cryogenic stress, became an invaluable gift to a new generation of aerospace engineers. Private companies like SpaceX and Blue Origin meticulously studied the X-33's post-mortem, learning what not to do. They adopted a more conservative, iterative approach, choosing proven materials like aluminum-lithium alloys for their first reusable rockets before gradually introducing more advanced composites where they were better understood. The fiery ghost of the X-33's ambition, though never reaching orbit, helped light the way for the successful reusable rockets we see landing today, proving that in the relentless pursuit of progress, there is no such thing as a true dead end, only a difficult and necessary detour. For centuries, the thunderous, fiery fury of the rocket has been the only way we have known to break the bonds of Earth's gravity. It is a method of immense power, but also of immense waste and expense, burning through fortunes of fuel and hardware for every precious kilogram that reaches orbit. But what if there was another way, a quieter, gentler, and infinitely more elegant path to the stars? This is the promise of the space elevator, a concept so simple in its geometry and so revolutionary in its implications that it has captivated scientists and dreamers for over a century. The core idea is breathtakingly straightforward. Instead of fighting gravity with a violent, explosive struggle, you would simply take a ride straight up. Imagine a cable, a celestial tow line, tethered to the Earth's surface at one end and anchored far above by a massive counterweight in space, perhaps a captured asteroid or a specially constructed station. This taut ribbon would stretch an almost incomprehensible 62,000 miles into the sky, tracing a permanent road from our world into the cosmos. Electrically powered climbers like robotic freight trains would glide up and down this ribbon, carrying payloads, satellites, and eventually people into orbit for a fraction of the cost and energy of a conventional rocket launch. The sheer elegance of this concept is what makes it so compelling. A space elevator would transform access to space from a spectacular, high-stakes event into a routine, industrial process. The cost of delivering a kilogram to orbit could plummet from the current thousands of dollars to mere hundreds, or even less. This isn't just an incremental improvement. It would be a complete paradigm shift, opening the floodgates to a new era of space development. Suddenly, building large-scale solar power satellites, asteroid mining operations, or massive orbital colonies would move from the realm of fantasy into the domain of practical economics. The elevator would become a continuous conduit for humanity's expansion, a peaceful bridge to the heavens that never closes. The vision was first articulated by the pioneering Russian rocket scientist Konstantin Tsiolkovsky in 1895, inspired by the newly built Eiffel Tower. He saw it not as a mere structure, but as a symbol of humanity's ultimate ambition to reach beyond its cradle. For decades, the idea remained a fascinating thought experiment, a staple of science fiction that seemed forever out of reach. That changed in the late 1990s and 2000s, when NASA's Institute for Advanced Concepts began to treat it with serious scientific rigor. Studies and conferences were held, detailed engineering models were run, and the concept was dissected from every possible angle. The physics, surprisingly, checked out. The orbital mechanics of a geostationary tether are sound. The real and ultimately insurmountable problem was not the theory, but the material. Building the tether itself requires a substance with a tensile strength and lightness that defies nature. It would need to be stronger than diamond, lighter than aluminum, and flexible enough to withstand unimaginable stresses from gravity, centrifugal force, and atmospheric weather. For a time, the only candidate that seemed to hold this miraculous promise was the carbon nanotube, a theoretical wonder material that, on paper, possessed the necessary properties. The space elevator became synonymous with the promise of nanotechnology, its entire future hinging on a material that scientists were still struggling to create in strands longer than a few centimeters in a laboratory. This is where the dream, for now, remains grounded. Despite decades of research, we have been unable to manufacture macroscopic quantities of perfect carbon nanotubes, let alone weave them into a cable tens of thousands of miles long. The material science challenges are simply too profound for our current capabilities. Furthermore, other daunting practicalities emerged from the NASA studies. The constant threat of micrometeoroid impacts shredding the ribbon, the peril of navigation and aircraft, and the terrifying political implications of such a permanent, fixed structure connecting Earth to space. Yet the space elevator endures. It persists not as a failed project, but as a North Star for materials scientists and futurists. It represents a clear, tangible goal, a benchmark for what our civilization could achieve if we could master matter at the molecular level. Its continued allure challenges us to think beyond the fiery, explosive traditions of rocketry, and to imagine a future where reaching orbit is as simple and unremarkable as riding an elevator to the top floor of a skyscraper, a silent testament to the power of an idea so elegant that it refuses to be forgotten. At first glance, it seemed like a case of blatant imitation. When the American space shuttle began flying in 1981, the Soviet leadership viewed it not as a vehicle of exploration, but as a potential weapon. Their military analysts became convinced that its large payload bay and ability to return to Earth were designed for sinister purposes, to swoop down, snatch Soviet satellites out of orbit, or even to deliver nuclear weapons in a surprise attack. This profound misreading of NASA intentions triggered a panicked response from the Kremlin, demanding that Soviet industry produce its own answer. The result, after years of secret development, was the Buran, which means snowstorm. And while it bore a stunning visual resemblance to its American cousin, Under the Skin, it was an entirely different and in many ways more sophisticated machine. The external similarity was purely a product of physics, not espionage. The laws of aerodynamics dictate a certain optimal shape for a reusable spacecraft that must survive re-entry and glide to a landing, which is why both vehicles ended up with a similar winged orbiter design. But the Buran was far from a simple copy. It was a product of the Soviet philosophy of engineering, robust, automated, and in some key areas vastly superior. The most jaw-dropping difference was its capability for fully unmanned, completely autonomous flight. Unlike the American shuttle, which required a crew for every mission, Buran could fly, dock with a space station, and return to Earth entirely under the control of its onboard computers. Its first and only flight in November 1988 was a breathtaking demonstration of this technology. With no one on board, it launched atop the monstrously powerful Energy rocket, completed 2 orbits of the Earth, and then, in a feat that stunned Western observers, landed automatically on a runway in Kazakhstan, having withstood crosswinds that would have challenged a human pilot. Its payload capacity was another area of superiority. While the US Shuttle was an integral part of its own launch system, with engines mounted on the orbiter itself, Buran was simply a payload. It was designed to sit atop the Energy, which was a standalone super-heavy lift rocket capable of launching over 100 tons to orbit with or without the shuttle attached. This meant Buran could carry a heavier payload into space than its American counterpart, and the Energy rocket itself represented a flexible launch system that could have been used for a variety of massive missions, from interplanetary probes to components of a large space station. For a brief, shining moment, it seemed the Soviet Union had not just caught up to American spaceplane technology, but had genuinely surpassed it, creating a more versatile and advanced system. But that moment was incredibly short-lived. The Buran program was born from the paranoid, overspent final days of the Soviet Union, and it was killed by the entity's collapse. The single flawless flight occurred just as the entire political and economic foundation of the nation was crumbling. The immense cost of developing both the Buran and the Energy rocket, a project that drained billions of rubles from an already strained economy, was simply unsustainable. With the dissolution of the USSR in 1991, the new Russian government, facing hyperinflation and social chaos, had no money or political will to continue a shuttle program whose primary justification, competing with America, had suddenly vanished. The program was abruptly cancelled, and the magnificent hardware was left to the mercy of the elements and neglect. The fate of the Buran orbiters and their supporting infrastructure is one of the most tragic stories in the history of spaceflight. The one vehicle that flew was placed in a storage hangar which collapsed in 2002 due to poor maintenance, destroying the orbiter and killing 8 workers. Other completed orbiters and test models were left to rust in open fields, their advanced carbon composite skins peeling away under the sun and rain. Some were repurposed as dismal tourist attractions in Moscow parks, while others were sold off for scrap. The enormous Energy rockets meant to launch them were cannibalized or left to decay in warehouses. This wasn't just the cancellation of a project. It was the wholesale erasure of a world-class technological achievement, a tangible symbol of how quickly political upheaval can dismantle decades of effort and investment. The story of Buran is a sobering reminder that the greatest threat to a grand vision in space may not be the vacuum of space or the limits of engineering, but the shifting sands of history here on Earth. While the Buran was a victim of earthly politics, another project was being conceived that aimed to venture further into our solar system than any spacecraft before it, driven by one of the most powerful and controversial technologies ever developed. In the early 2000s, NASA planners were setting their sights on the outer planets, specifically the captivating icy moons of Jupiter, Europa, Ganymede, and Callisto. For decades, evidence had been mounting that these frozen worlds were not barren balls of rock and ice, but rather held vast, global oceans of liquid water hidden beneath their cracked, icy shells. The implications were, and still are, staggering. Where there is liquid water, there is the potential for life as we know it. The scientific desire to explore these alien oceans was overwhelming, but reaching them presented a monumental challenge. The immense distance from the sun makes solar power virtually useless, and the journey time using conventional chemical propulsion would be measured in many years, even decades. To solve this, NASA turned to a technology that promised to cut the travel time in half and provide ample power for a suite of powerful instruments: nuclear fission. The mission was named the Jupiter Icy Moons Orbiter, or JIMO, and it was designed to be a flagship mission in the truest sense of the word. This was not a small, modest probe. It was envisioned as a behemoth of scientific exploration, a spacecraft that would revolutionize our understanding of the outer solar system. At its heart was a revolutionary propulsion system, a nuclear fission reactor that would power a set of ion thrusters. Unlike the brief, explosive burns of chemical rockets, these ion engines would provide a gentle, continuous thrust for months or even years on end, efficiently accelerating the massive craft to incredible speeds. This nuclear electric propulsion system was the key that would unlock the outer planets, turning a 15-year journey into a more manageable 7- or 8-year voyage. Once it arrived in the Jovian system, the reactor would continue to provide a bonanza of electrical power, enough to operate power-hungry instruments like heavy-duty ice-penetrating radar to map the subsurface oceans, powerful lasers to vaporize surface ice for analysis, and high-resolution cameras to map the complex geology of each moon in stunning detail. The ambition didn't stop there. JIMO was designed to be a multi-moon tour de force. It wouldn't just fly past these worlds. It would enter orbit around each one sequentially, spending months at Europa, then Ganymede, then Callisto, conducting an unprecedented in-depth survey. It would have been the most capable and powerful deep space probe ever conceived, a robotic ambassador capable of answering the most profound question we can ask: are we alone in the universe? The scientific community was electrified by the prospect. Here was a mission that could finally probe the depths of Europa's hidden ocean, potentially detecting the chemical signatures of biological activity, or even mapping the topography of the seafloor itself. It represented a quantum leap in planetary science, a mission that would have dwarfed the capabilities of the Voyagers, Galileo, and Cassini combined. However, the very thing that made JIMO so powerful was also its greatest liability: its nuclear reactor. The plan called for launching a significant quantity of highly enriched uranium into space on a brand new, untested rocket. The public and political perception of this risk was immediate and intense. The memory of previous nuclear accidents, like the Soviet Cosmos satellite that scattered radioactive debris over Canada, was still fresh. Environmental groups and a skeptical public raised the nightmarish scenario of a launch failure, where a rocket explosion could disperse radioactive material across a wide area of Florida or the ocean. NASA engineers argued that the reactor would be launched in a cold state, meaning it would not be turned on and become radioactive until it was safely in a high, stable orbit far from Earth. They designed robust containment systems to survive a catastrophic launch explosion, but the fear, once ignited, was difficult to extinguish. The words nuclear and rocket together proved to be a public relations challenge too great to overcome. Compounding the public fear was the sheer, escalating cost of such a complex and technologically ambitious mission. As development progressed, the estimated price tag ballooned into the tens of billions of dollars, making it one of the most expensive space missions ever proposed. In 2005, facing these twin pressures of immense cost and potent public anxiety, the newly elected administration of President George W. Bush made the difficult decision to cancel the JIMO project. The plug was pulled, and the dream of a nuclear-powered tour of Jupiter's moons was shelved indefinitely. Yet, the scientific goals of JIMO were far too compelling to simply abandon. Its legacy did not die with its cancellation. Instead, its spirit was fractured and distilled into a new generation of missions. The desire to explore Europa specifically gave birth to the Europa Clipper mission, which adopts a safer, more focused approach. Instead of nuclear power, it uses massive solar arrays, a testament to the incredible advances in solar cell efficiency since the 2000s. And instead of orbiting Europa directly, which would expose it to the planet's punishing radiation belts, it will perform numerous close flybys. While not as capable as JIMO would have been, Europa Clipper is a direct descendant, a pragmatic and politically viable incarnation of that original, grand nuclear-powered vision. The story of JIMO is a classic and poignant example of how the most scientifically breathtaking missions can be grounded not by a failure of engineering, but by the powerful forces of public perception and budgetary reality, forcing brilliant minds to find quieter, smarter, and safer ways to chase the same profound truths. Of all the complex machinery required to put a human on another world, perhaps none is more personal and more critical than the spacesuit. It is not merely a garment, it is a wearable spacecraft, a delicate bubble of Earth-like environment that must protect its occupant from the absolute hostility of an alien world. For Mars, this challenge is magnified to an almost terrifying degree. The planet presents a unique cocktail of dangers, crushing low-pressure, toxic dust that is as fine as talcum powder and electrostatically charged, extreme temperature swings, and relentless radiation unshielded by a global magnetic field. The suits worn by the Apollo astronauts on the Moon were magnificent achievements for their time, but they were also cumbersome, restrictive, and designed for short-term, low-gravity excursions. For the multi-year Mars missions envisioned, where astronauts will need to conduct complex geological fieldwork for hours at a time over many months, a new generation of suit was required, one that was not just protective but empowering. This was the goal behind the advanced Martian spacesuit concepts, designs that pushed the very boundaries of biomechanics and life support, only to be sidelined by the shifting winds of space policy. The most visionary of these designs looked less like a traditional puffy suit and more like something from a science fiction epic, incorporating a hard composite torso shell and revolutionary soft robotics. The key innovation was the integration of a lightweight exoskeleton, not unlike the powered frames being developed for terrestrial medical and military applications. On Mars, where gravity is roughly 1/3 of Earth's, the primary purpose wouldn't be to grant superhuman strength, but to provide crucial support and counteract the suit's inherent internal pressure. A pressurized suit naturally wants to assume a rigid, inflated shape, forcing an astronaut to constantly fight against it just to bend an elbow or knee, an exhausting endeavor that wastes precious energy and leads to rapid fatigue. The exoskeleton would solve this by providing powered assistance at the joints, making movement feel almost natural. A subtle servo motor at the knee would help the astronaut bend and squat to collect a rock sample. Actuators in the shoulders and wrists would counteract the suit's resistance, allowing for delicate manipulation of tools with a level of precision previously impossible. This wasn't about creating super soldiers. It was about creating scientist explorers who could work effectively and safely in an environment that wants to cripple them with every step. Beyond mobility, the life support systems within these proposed suits represented a quantum leap over existing technology. The portable life support system on an Apollo suit was essentially an open-loop system. It would scrub carbon dioxide and cool the astronaut, but it constantly vented moisture and oxygen wastefully into the void. For a mission to Mars where every gram of water and oxygen must be conserved or manufactured on site, such profligacy is unacceptable. The new Martian suits were designed as closed-loop regenerative systems. They would utilize advanced solid amine swings to more efficiently capture carbon dioxide, and then employ sophisticated Bosch or Sabatier reactors to potentially convert that waste carbon dioxide back into breathable oxygen. Water recovered from the astronauts' sweat and breath would be purified and recycled within the suit itself, creating a nearly self-sustaining microecology. This focus on sustainability transformed the suit from a life-preserving consumable into a miniature prototype of the larger closed-loop habitats the astronauts would live in, a critical testbed for the technologies that would allow humanity to truly live off the land on another planet. Despite the clear and present need, the full-scale development of these advanced suits has been repeatedly deferred. The primary reason is a classic tale of programmatic prioritization. Major space initiatives, especially those funded by government agencies, are often driven by a single, overarching goal, the core mission. For decades, that goal has oscillated between Mars and the Moon. When the political priority shifts, as it did from the Constellation program's Mars focus to the Artemis program's lunar return, the funding and urgency immediately flow toward the primary objective. The Lunar Gateway Station, new lunar landers, and the Orion capsule become the priorities. Supporting technologies, even those as critical as the spacesuit, are often seen as secondary items that can be developed later. This creates a dangerous lag where the vehicle to get to the destination is being built long before the suit needed to step outside on that destination is fully funded. It's a paradox of planning. We design the rocket before we design the boots that will take the first step. This delay has real consequences. It risks creating a scenario where astronauts finally arrive at Mars, only to be forced to conduct surface operations in suits that are only marginally better than those used on the Moon 50 years prior, severely limiting their scientific return and increasing their physical risk. The story of the advanced Martian suit is a powerful lesson in systems engineering, reminding us that a mission is only as strong as its most neglected component, and that the technology that interfaces directly with the human body is often the one that deserves the most forethought, not an afterthought. While we grapple with the immediate challenges of keeping astronauts alive just beyond our atmosphere, other visionaries were looking far further ahead, asking a question that redefines the very concept of a frontier. What if humanity's future in space wasn't about temporary outposts or cramped stations, but about building entirely new Earths? This was the breathtakingly ambitious question posed by physicist Gerard K. O'Neill in the 1970s. Disillusioned by the ecological and social problems plaguing our planet, O'Neill didn't just dream of visiting space, he dreamed of moving in. His answer was not a planet, but a masterpiece of orbital engineering. The O'Neill cylinder, a space colony designed not for dozens, but for tens of thousands of permanent residents. The design itself was a work of art, solving the problems of space living with elegant, gravity-defying solutions. Imagine two gigantic cylinders, each 20 miles long and 5 miles in diameter, rotating in opposite directions to cancel out gyroscopic effects. They would be connected at their ends by a central bearing system, floating in the void at a stable Lagrange point, balanced between the gravitational pulls of the Earth and the Moon. Inside, the entire inner surface of these colossal tubes would be transformed into a living landscape. Through the magic of centrifugal force, the rotation would create a sensation of normal Earth gravity along the inner hull. The most mind-bending part of the design was the interior layout. The land would be on the inside of the curve. You could look up from your backyard and see other fields, rivers, and towns stretching overhead, connected by graceful bridges, all bathed in the constant, reflected light of massive mirrors that would simulate a perfect 24-hour day-night cycle. These wouldn't be sterile metal cans. They would be verdant, open-world ecosystems complete with agriculture, forests, bodies of water, and weather systems, all contained within a carefully balanced biosphere. O'Neill's vision was not just an architectural blueprint. It was a complete socio-economic plan for a post-planetary society. He calculated that the materials to build these vast arcs could be mined from the moon or nearby asteroids, launched into space using a mass driver, a type of electromagnetic catapult, at a fraction of the cost of launching resources from Earth's deep gravity well. The colonies would be economically self-sufficient, building upon a space-based manufacturing industry that could create products impossible to make on Earth, from perfect ball bearings to revolutionary pharmaceuticals, in the pristine environment of microgravity. He saw these cylinders not as escape pods for a privileged few, but as a new frontier that could alleviate terrestrial pressures like overpopulation and resource scarcity, offering millions of people a chance at a new life with a higher standard of living, all while allowing our home planet to heal. For a moment in the 70s, this future seemed almost within grasp. O'Neill's ideas, popularized through his book, The High Frontier, and a series of NASA summer studies, captured the public imagination and inspired a generation of engineers and scientists. The concept was technically sound, grounded in known physics, and presented with a compelling urgency. Yet the sheer, staggering scale of the endeavor ultimately proved to be its downfall. The financial cost of bootstrapping an entire space-based mining and manufacturing industry was estimated to be in the trillions of dollars, a sum that made even the Apollo program look like a modest down payment. The political will for such a monumental, long-term project evaporated as the space race cooled and national priorities turned inward. The technology for large-scale autonomous construction in space was, and in many ways still is, a distant dream. The O'Neill cylinder was an idea born from the optimistic, can-do spirit of the Apollo era, but it quickly became a symbol of a future that was simply too big, too expensive, and too complex for its time. But to dismiss O'Neill's cylinders as a forgotten fantasy is to profoundly misunderstand their enduring power. While the specific blueprint may remain on the drawing board, the philosophical core of his vision is more alive today than ever before. He fundamentally shifted the conversation from "how do we survive in space" to "how do we live in space?" His work is the direct intellectual ancestor of every concept for large-scale space habitats, from the rotating modules proposed for future Mars missions to the orbital hotels envisioned by private companies. He gave us permission to think on a planetary scale, to imagine engineering entire worlds rather than just visiting them. The O'Neill cylinder remains the North Star for a future where humanity is no longer confined to a single, fragile planet, but is truly free to choose its home among the stars, a timeless challenge to never stop thinking big. Following the monumental achievements of Apollo, NASA entered a period often described as a lingering pause in human deep space exploration, with decades spent perfecting operations in low Earth orbit aboard the Space Shuttle and the International Space Station. But in 2005, a powerful new vision was born, one that aimed to reignite the fiery ambition of the 1960s and propel astronauts back to the lunar surface and onward to the Red Planet. This was the Constellation program, a sweeping, multi-billion-dollar initiative announced by President George W. Bush with the clear and ambitious goals of retiring the aging space shuttle fleet, returning Americans to the moon by 2020, and establishing a permanent lunar outpost as a stepping stone for the ultimate prize, a human mission to Mars. The hardware designed to achieve this was a family of vehicles that echoed the past while reaching for the future. At its heart was the Orion spacecraft, a robust, cone-shaped crew capsule that looked strikingly similar to the iconic Apollo command module, but was significantly larger, designed to support 4 astronauts for missions lasting up to 6 months. To launch Orion and its heavy cargo, NASA began developing the Ares family of rockets. The Ares 1 was a towering, sleek launcher consisting of a single space shuttle solid rocket booster with a second stage on top, tasked with carrying the Orion crew capsule into orbit. For the heavy lifting of lunar landers and habitat modules, NASA envisioned the Ares 5, an absolute behemoth of a rocket that would have been the most powerful launch vehicle ever built, surpassing even the mighty Saturn V. Its design was a masterpiece of efficiency, repurposing existing space shuttle technology like its main engines and solid rocket boosters, but scaling them up to create a new Titan. The plan was for Orion to dock in Earth orbit with a lunar lander launched separately by the Ares 5, a complex orbital rendezvous that mirrored the Apollo method but on a grander, more sustainable scale. For a few years, the Constellation program surged forward with tremendous momentum. Billions of dollars were invested, and across the country, aerospace contractors ramped up hiring. Test flights were conducted, including a successful launch of the Ares 1X test vehicle in 2009, a spectacular sight that seemed to herald a new era. However, almost from its inception, Constellation was plagued by a host of formidable challenges. The program struggled with immense technical complexities and significant cost overruns, its budget ballooning as the intricate development of 2 entirely new rocket systems proceeded. Perhaps more critically, it found itself trapped in a political quicksand. The vision for deep space exploration, while inspiring, was subject to the fickle winds of Washington, D.C. policy and the nation's financial health. The 2008 global financial crisis placed enormous pressure on government spending, and every major federal program came under intense scrutiny. The program's fate was ultimately sealed by a change in administration and a fundamental shift in national priorities. When President Barack Obama took office in 2009, he ordered a comprehensive review of the nation's human spaceflight plans. The resulting report was brutally critical, finding Constellation to be severely underfunded, behind schedule, and on an unsustainable trajectory. In 2010, the Obama administration made the difficult decision to cancel the program, arguing that it was sucking the oxygen out of NASA's budget and stifling innovation. The cancellation was met with fierce opposition from some in Congress and within the aerospace community, where thousands of jobs were suddenly in jeopardy. It was a stark and painful reminder that a space program's success depends as much on unwavering political and financial support as it does on engineering brilliance. Yet the story of Constellation does not end with its cancellation. In the world of government spaceflight, grand programs rarely die completely. Instead, they often undergo a strange and iterative metamorphosis. The core technological investments and hard-won engineering from Constellation were far too valuable to simply discard. The Orion crew capsule, then known as the Orion Crew Exploration Vehicle, was spared from the scrap heap. Its development continued, evolving from a lunar-focused vehicle into the multi-purpose deep spacecraft it is today. The concept of a heavy-lift rocket also survived, though its design was radically altered. Out of the ashes of the Ares 5 rose the Space Launch System, or SLS, a new super-heavy-lift rocket that incorporated much of the knowledge gained from its predecessor. This phoenix-like rise from cancellation to rebirth illustrates a crucial truth about the long arc of space exploration. Ambition is cyclical, not linear. Today's Artemis program, with its SLS rocket and Orion capsule now flying, is the direct descendant of Constellation. It carries the same core goals, returning to the Moon and preparing for Mars, but approaches them with a new architecture involving a lunar gateway station and a stronger emphasis on commercial and international partnerships. The journey was not a straight line, but the destination remained, proving that even when a specific path is closed, the collective dream of exploration finds a way to endure and adapt. While American astronauts were bouncing across the lunar regolith in their open-top, battery-powered lunar roving vehicle, Soviet engineers were putting the finishing touches on a machine that represented a completely different, and in many ways far more ambitious, vision for exploring another world. The Soviet lunar rover, known as the Lunokhod, was not a car for cosmonauts. It was a sophisticated, self-driving robotic laboratory. But hidden away in their design bureaus was an even more audacious vehicle, one that was never publicly acknowledged during the space race. This was the true Soviet answer to the American LRV, a pressurized one-man rover designed for a cosmonaut to drive across the moon in a shirt-sleeve environment, a rolling habitat that combined the freedom of a car with the safety of a spacesuit. Its official designation was the Lunar Expeditionary Vehicle, but its informal name captured its purpose perfectly: the Lunokhod crewed variant, or more romantically, the Moonwalker. This vehicle was a masterpiece of cramped, efficient engineering, where the American rover was an open dune buggy that required its drivers to remain in their full, bulky spacesuits for the entire journey. The Soviet design featured a small, pressurized cabin. A single cosmonaut would sit inside this sealed pod, controlling the vehicle with a joystick while looking out through large, panoramic windows. He would be free to work in a comfortable, shirt-sleeve environment, his only connection to the outside being a rear airlock hatch through which he could exit for surface activities. This design solved one of the biggest limitations of the American missions: astronaut fatigue. Driving the American rover in a stiff, pressurized suit was exhausting work. The Soviet vehicle eliminated that strain, allowing for longer, more productive traverses. Its range was projected to be far greater than that of the American LRV, enabling journeys of dozens of miles from the landing site, a capability that would have dramatically expanded the scientific return of a single mission. The rover's intended mission profile was a story in itself. It wasn't designed to be driven off a porch like the American version. Instead, the entire lunar lander would itself serve as the rover's garage. After a soft landing on the moon, the side of the lander would open up, and a sophisticated ramp system would gently lower the folded rover directly onto the surface. The cosmonaut would then enter the vehicle through the connecting airlock, power up its systems, and simply drive away, a lone explorer in a mobile base. The plan called for geological surveys that could last for days, with the driver conducting experiments from the safety of his cabin or suiting up to collect samples from particularly interesting sites. It was a vision of lunar exploration that was less about quick jaunts and flag planting, and more about serious, prolonged scientific fieldwork, a testament to the Soviet program's often underappreciated focus on robotic and scientific precision. Today, this remarkable vehicle is not resting on the moon, but sitting silently in a museum outside of Moscow. It is a pristine, fully functional artifact of a future that never was, a haunting symbol of lost potential. Its existence is a direct and poignant consequence of the repeated, catastrophic failure of the N-1 rocket. Without that colossal launcher to deliver the heavy lander and its rover to the moon, the vehicle had no purpose. It was never needed, and so it never flew. Seeing it today, one is struck by its clever design and its palpable sense of readiness, a machine forever waiting for a launch that was permanently scrubbed. It stands as a powerful, metallic ghost of the Cold War, a perfect representation of how a single point of failure, a rocket that refused to fly, can unravel an entire web of brilliant technology, leaving behind museum pieces where there should have been milestones. For centuries, one of humanity's most profound questions has lingered unanswered in the dark. Are we alone? Is Earth a singular miracle, or is our galaxy quietly teeming with other worlds like our own? By the late 1990s, with the first detections of exoplanets around distant stars, that question shifted from pure philosophy to a tangible scientific goal. We knew these worlds were out there, but they were invisible to us, tiny specks lost in the blinding glare of their parent stars. To truly find an answer, we needed a telescope that could perform the ultimate feat of astronomical gymnastics: block out that starlight and take a direct picture of a pale blue dot orbiting another sun. This was the monumental ambition of the Terrestrial Planet Finder, or TPF, a mission designed not just to see these worlds, but to study them, to analyze the chemical composition of their atmospheres, and to search for the telltale signs of life. The concept behind TPF was as brilliant as it was challenging. It wasn't conceived as a single telescope, but as a suite of two complementary observatories, each employing a different cutting-edge technology to achieve the same incredible goal. One concept involved a massive optical telescope with a coronagraph, an internal instrument designed to precisely block the light of the star, much like using your hand to shield your eyes from the sun to see something nearby. The other, even more ambitious design was for a formation-flying interferometer. This would use multiple smaller telescopes, flying in perfect, precise formation across thousands of kilometers of space, acting as one giant virtual mirror. By combining their light, this array would achieve a resolution so sharp it could distinguish a planet from its star, even across distances of dozens of light years. Both designs shared a common, breathtaking objective: to capture the first true family portrait of another solar system, and to analyze the faint light passing through a distant exoplanet's atmosphere, looking for the spectroscopic fingerprints of gases like oxygen, methane, and water vapor, the potential biosignatures of a living world. The scientific potential was quite simply revolutionary. TPF wouldn't just be counting planets, it would be a machine for discovery on a Copernican scale. It could have told us the average number of Earth-like planets in the habitable zone of Sun-like stars. It could have determined if worlds with atmospheric compositions similar to ours were common or incredibly rare. And if it found a world with an atmosphere rich in oxygen and methane gases that quickly react with each other and require a continuous biological source to maintain their presence, it would have provided the strongest possible evidence that life is not a fluke of Earth, but a common feature of the cosmos. The data would have transformed our understanding of our place in the universe, answering a question that has haunted humanity for millennia. Development moved forward with serious intent in the early 2000s. NASA invested significant funds into technology development, tackling the immense engineering challenges of building ultra-sensitive detectors and perfecting the formation flying algorithms. The project had strong support from the scientific community and was given a tentative launch date sometime in the 2020s. The roadmap was clear and the momentum was building. Then, the financial reality of ambitious space science collided with shifting national priorities. The projected cost of TPF ballooned into the billions, and in an era of tightening budgets and the rising costs of the Iraq War and other terrestrial concerns, NASA's budget for astrophysics was squeezed. The mission was deemed too expensive, too risky, and its timeline too long. In 2006, it was quietly postponed indefinitely, its funding reallocated to other projects. It was a classic casualty of the perennial tension in big science between boundless ambition and finite resources. Yet, the dream that TPF represented never died. Its scientific goals were so compelling that they became the driving force behind the next generation of space telescopes. The James Webb Space Telescope, while not designed as a direct planet imager, carries instruments that can perform rudimentary atmospheric spectroscopy on larger exoplanets, a first step toward TPF's grand vision. Even more directly, the Nancy Grace Roman Space Telescope, set to launch later this decade, will carry an advanced coronagraph technology demonstrator, a direct descendant of the TPF research, that will test the critical starlight blocking techniques needed for a future planet finder. And now, new mission concepts like the Habitable Worlds Observatory, which NASA has slated for the 2040s, have explicitly adopted the original mandate of TPF. The Terrestrial Planet Finder was not a failure. It was a visionary seed planted too early. Its postponement highlights how the most profound scientific quests can be delayed by earthly budgets, but its enduring legacy proves that a question as powerful as "Are we alone?" will always find a new telescope and a new generation of explorers to chase the answer. In the high-stakes final act of the Cold War, a new and terrifying front opened not on Earth, but in the imagined battlefield of space. In 1983, President Ronald Reagan stood before the American people and unveiled a vision so technologically audacious and strategically radical that it seemed ripped from the pages of a science fiction novel. He called it the Strategic Defense Initiative, but the world would forever know it by the name given by its critics, Star Wars. The core premise was a complete departure from the grim doctrine of mutually assured destruction that had kept the peace for decades. Instead of relying on the threat of devastating retaliation, SDI proposed a defensive shield, a network of space-based battle stations armed with hyper-advanced lasers, particle beams, and kinetic interceptors that could supposedly detect, track, and destroy thousands of incoming Soviet ICBM in the blink of an eye, rendering nuclear weapons, in Reagan's own words, impotent and obsolete. The sheer scale of the proposed system was beyond anything ever contemplated. Imagine a constellation of dozens, perhaps hundreds, of powerful satellites constantly orbiting the Earth, their sensitive sensors perpetually scanning the skies for the telltale heat signature of a missile launch. Upon detection, these robotic sentinels would spring into action. One concept involved chemical lasers, massive structures that would mix fuels to create a devastating beam of energy capable of vaporizing a warhead thousands of miles away. Another, even more futuristic idea was the nuclear-pumped X-ray laser. This involved detonating a small nuclear device in space. The explosion would power a series of laser rods that would then fire intense pulses of X-rays at multiple targets simultaneously. It was a weapon born from the mind of physicist Edward Teller, a concept so powerful and terrifying it bordered on the apocalyptic. The entire architecture was a layered defense, designed to intercept missiles in their boost phase as they rose from their silos, in their mid-course phase as they sailed through the vacuum of space, and finally in their terminal phase as they re-entered the atmosphere. It was a perfect leak-proof shield, at least on paper. The technical hurdles, however, were so immense they were practically insurmountable with 1980s technology. The computing power required to manage the battle management software to track thousands of objects, distinguish real warheads from decoys, and coordinate the response of hundreds of individual weapons across the globe in mere minutes was a problem that dwarfed anything ever attempted. The lasers themselves required mirror optics of unimaginable size and precision, and the energy needed to power them would have required massive, non-existent space-based power plants. Furthermore, the system would have to be essentially perfect. Even a 99% success rate would mean dozens of nuclear warheads could still slip through the shield, resulting in catastrophic destruction. Critics, including many prominent scientists, argued it was a fantastical pipe dream, a multi-hundred-billion-dollar project that would never work as advertised and would only serve to escalate the arms race to dangerous new heights. Yet, for all its science fiction overtones and strategic controversy, the Strategic Defense Initiative had a profound and unintended consequence. The immense political will and funding behind it acted as a massive gravitational force, pulling an entire generation of cutting-edge technologies into development at an accelerated pace. To make SDI even remotely plausible, scientists had to make quantum leaps in areas like high-speed computing, sensor technology, and advanced optics. The need for smaller, more powerful computers to handle the data processing directly fueled the microchip revolution. The research into laser pointing and tracking systems led to breakthroughs in precision guidance and medical imaging. The development of new composite materials and lightweight mirrors for the space-based components found applications in everything from astronomy to telecommunications. While the Star Wars shield itself was never built, the technological seeds it planted grew into the bedrock of our modern digital world. The ultimate fate of SDI was sealed not by its technical challenges, but by the sudden and unexpected end of the Cold War. With the collapse of the Soviet Union and the dissipation of the immediate nuclear threat, the overwhelming political urgency for such a system evaporated. The program was dramatically scaled back, its ambitions curtailed and repurposed into more modest, ground-based missile defense systems that are still in use today. The grand vision of a perfect celestial shield faded into history, but its legacy is a powerful and complex one. It stands as the ultimate example of how a driver as potent as military necessity can pour fuel on the fires of innovation, achieving spectacular technological spin-offs even when the original, terrifying goal remains forever out of reach. It was a project born from fear that ultimately helped build the tools for a more connected world, a paradoxical testament to the unpredictable path of progress. While astronauts were capturing the world's imagination with their moonwalks, a quieter but equally profound scientific revolution was being planned for the Apollo program, one that had its sights set not on the lunar surface, but on our own life-giving star. This was the Apollo Telescope Mount, a sophisticated solar observatory originally designed to fly on one of the later Apollo missions, perhaps even on a dedicated orbital workshop made from a converted Saturn rocket stage. Its purpose was to give scientists an unprecedented, stable platform above Earth's distorting atmosphere, allowing them to study the sun in wavelengths of light we can't see from the ground, and to observe solar flares and other phenomena with a clarity never before possible. The ATM was a complex instrument package, a battery of telescopes and spectrographs specifically tuned to unravel the secrets of solar physics, representing a giant leap in our understanding of the forces that govern our corner of the cosmos. But as the Apollo program faced budget cuts and mission cancellations following the successful lunar landings, the future of this powerful observatory was thrown into jeopardy. Rather than let the hardware go to waste, NASA's brilliant engineers performed a remarkable act of scientific improvisation. They took the Apollo Telescope Mount and made it the centerpiece of America's first space station, Skylab. Launched in 1973, Skylab provided the perfect home for the ATM. Mounted on a truss structure outside the station's main workshop, it became an external observatory that astronauts could operate from inside for months at a time. The results were nothing short of transformative. Over the course of 3 crewed missions, the ATM returned a treasure trove of data, capturing over 150,000 images of the sun and providing our first detailed look at the corona, solar flares, and the sun's complex magnetic fields. It revolutionized solar physics, delivering science far beyond what its original Apollo-bound design had envisioned. This success, however, only hinted at the even grander ambitions that had been left on the drawing board. The original vision for the ATM wasn't just a one-off instrument for a temporary station. It was conceived as the prototype for a future fleet of free-flying, automated solar observatories. Scientists dreamed of dedicated satellites built on the same proven principles as the ATM that could maintain a constant, unwavering watch on the Sun. These advanced platforms would provide continuous monitoring of solar weather, giving crucial early warning of the coronal mass ejections and solar flares that can disrupt power grids, disable satellites, and endanger astronauts with bursts of radiation. This dream of a permanent solar sentinel in orbit was the logical next step, a way to turn the ATM's temporary success into a permanent new window on our star. Yet this future never materialized. In the austere budgetary environment that followed the end of Apollo and Skylab, NASA priorities underwent a dramatic shift. The limited funding available was funneled into the development of the Space Shuttle, a new transportation system that promised to make access to space routine and affordable. Grand plans for dedicated science platforms, including the advanced solar observatories, were deemed too expensive and too specialized. The scientific community had to make do with smaller, less capable telescopes that could be launched as secondary payloads or housed inside the shuttle's cargo bay for short-duration missions. The full potential of the Apollo telescope, Mount's design, its ability to serve as the foundation for a new era of heliophysics, remained frustratingly untapped, a testament to how even the most successful scientific tools can have their promise curtailed when political and financial winds change direction. The story of the ATM is a powerful lesson in adaptation and lost opportunity. It shows how a scientific instrument can be saved from cancellation through clever repurposing, achieving great things in a role it was never originally intended for. But it also underscores a recurring theme in space exploration: the constant tension between foundational science and the infrastructure required to pursue it. We often choose to build the highway before we decide on the destination, and in doing so, we can leave behind the blueprints for vehicles that might have taken us to incredible places. This pivot from understanding the Sun to focusing on the means of transportation sets the stage for our next project, which turned its focus inward, seeking to understand not the cosmos, but the human body's ability to survive within it. For all the ambitious plans to build interplanetary arcs and giant space stations, one of the most critical pieces of the deep space puzzle remains frustratingly incomplete: understanding exactly what long-term weightlessness does to the human body and how we might counteract it. We've known for decades that prolonged exposure to microgravity wreaks havoc on our biology. Astronauts on the International Space Station experience muscle atrophy, bone density loss equivalent to decades of aging, and concerning changes to their vision and cardiovascular systems. These are manageable risks for a 6-month tour aboard the ISS, but they become absolute showstoppers for a multi-year journey to Mars. How do you keep a crew healthy and functional when their very cells are rebelling against the alien environment of deep space? NASA had a brilliant, elegant, and thoroughly tested solution ready to go, a piece of hardware that was designed to provide the answers. It was called the Centrifuge Accommodations module, and its story is one of the most poignant what-ifs in the history of space medicine. The CAM was not some abstract concept. It was a real, built and tested module, a scientific instrument of incredible value. Imagine a large, sophisticated laboratory rack, but one that spun. Inside its rotating drum, NASA planned to house a menagerie of biological specimens from mice and rats to plants and insects, and subject them to varying levels of artificial gravity. This was the true genius of the design. The centrifuge wasn't set to just one speed simulating Earth gravity. Researchers could dial it down to simulate Martian gravity, which is about 38% of Earth's, or lunar gravity at 17%. For the first time, we wouldn't just be studying the effects of weightlessness. We would be conducting controlled experiments to find the precise dosage of gravity required to maintain health. What is the minimum amount of spin needed to keep bones from dissolving? Could astronauts on a Mars mission get by with a short daily jog in a centrifuge, rather than the 2 hours of strenuous daily exercise currently required on the ISS? The CAM was the key that would unlock these answers, providing the essential data to design the habitats and spacecraft for the long journeys to come. The module was a cornerstone of the original ISS design, a critical part of the station's purpose as a testbed for future exploration. It was built by the Japanese space agency, JAXA, and was fully certified for flight. It wasn't a prototype, it was flight-ready hardware sitting in a clean room waiting for its ride to orbit. But that ride never came. As the costs of building and operating the International Space Station spiraled upward, something had to give. The station's budget was hemorrhaging, and NASA was forced to make a series of heartbreaking triage decisions. Grand, scientifically vital components were deemed expendable. The CAM, with its significant mass and operational complexity, was seen as a luxury that could be cut to save money. In 2005, the module was officially cancelled. The decision was purely financial, a classic example of sacrificing long-term preparedness for short-term budgetary relief. The completed billion-dollar module was put into storage and then eventually given to a museum. It now sits as a silent, gleaming exhibit, a monument to a crucial set of questions we deliberately chose not to answer. The cancellation of the Centrifuge Accommodations module left a gaping hole in our knowledge that we are still struggling to fill today. We are now planning missions to Mars with essentially the same incomplete understanding of human physiology in partial gravity that we had 20 years ago. We are making educated guesses based on the devastating effects of zero-G and the limited data we have from Earth-based bed rest studies, but we are fundamentally flying blind. Every architectural drawing for a Mars transfer vehicle or a lunar base that includes artificial gravity is based on theoretical models, not hard data from the CM we never launched. This missed opportunity forces us to be overly cautious, to pack more exercise equipment and medical supplies, and to accept a higher level of risk for the astronauts who will make those journeys. It is a stark reminder that in spaceflight, the supporting research, the unglamorous foundational science, is not a secondary concern. It is the very bedrock upon which all successful missions are built. Without it, we are engineering magnificent ships for a voyage into a physiological unknown. This focus on the fundamental systems needed for exploration leads us directly to another project that sought to redefine a different core technology, not how we live in space, but how we get there. For decades, the fundamental principle of rocketry has remained largely unchanged. Burn fuel, expel mass out the back, and ride the equal and opposite reaction forward. It's a powerful but brutally inefficient process, one that trades immense amounts of propellant for relatively modest gains in velocity. But what if we could break this tyrannical trade-off? What if we could create a rocket engine that uses energy far more judiciously? One that could gently but relentlessly push a spacecraft to incredible speeds without needing to carry a mountain of fuel. This is the revolutionary promise of the Variable Specific Impulse Magnetoplasma Rocket, or VASIMR, a propulsion technology that sounds like it belongs in a 23rd century starship, but was conceived in the late 1970s by former astronaut and plasma physicist Franklin Chang Diaz. The core concept of VASIMA is a masterclass in elegant engineering, replacing violent combustion with the serene power of magnetic fields. Imagine a three-stage process happening inside a specialized engine core. First, a neutral gas like argon or hydrogen is injected into a chamber where it is bombarded with radio waves, superheating it into a fourth state of matter, plasma. This isn't just hot gas, it's a soup of charged ions and electrons, a substance so energetic it would instantly vaporize any physical container it touched. This is where VASIMA genius truly shines. Instead of trying to contain this star-like material with physical walls, the engine uses incredibly powerful superconducting magnets to form an invisible, indestructible magnetic bottle. This contained plasma is then funneled through a second stage where it is heated even further, and finally, it is squirted out the back of the engine through a magnetic nozzle, creating a continuous, shimmering blue exhaust plume that pushes the spacecraft forward. The variable specific impulse part of its name is the key to its versatility, a feature no conventional chemical rocket can match. Specific impulse is essentially a measure of an engine's fuel efficiency. VASIMA can dial this up or down like a volume knob. Need to move a massive payload quickly but don't mind using more fuel, crank down the specific impulse for high thrust. On a long-duration mission where fuel conservation is paramount, like a trip to Mars, dial the specific impulse way up. In this high-efficiency mode, VASIMA would produce a very gentle thrust, so gentle you could barely feel it, but it could maintain that thrust continuously for months or even years on end. This is the magic of electric propulsion. While a chemical rocket provides a brief, explosive shove and then coasts for the entire journey, a VASIMA engine would be a constant companion, always accelerating, slowly but surely building up to breathtaking speeds. A manned mission to Mars using this technology could potentially cut the travel time from 8 months down to just 40, dramatically reducing the crew's exposure to deadly cosmic radiation and the debilitating effects of microgravity. The potential was so compelling that NASA invested significantly in its development through the 2000s. A $50,000 prototype was successfully tested on the International Space Station in 2015, a crucial demonstration that proved the core technology could operate in the vacuum of space. The path forward seemed clear: scale up the power. The real promise of VASIMA lies with nuclear power. Pairing the engine with a compact fission reactor could provide the megawatts of electricity needed to unleash its full potential, turning it into the workhorse engine for the solar system. Yet, despite its dazzling promise, VASIMA development within NASA hit a familiar wall: the cycle of shifting priorities and finite funding. As the agency's focus pivoted back to the Moon with the Artemis program, the sustained, long-term investment required to mature VASIMA from a brilliant prototype into a flight-ready engine failed to materialize. The project, deemed too forward-looking for NASA's immediate budgetary realities, was effectively shelved. But the story doesn't end there. In a powerful testament to its potential, Franklin Chang Diaz left NASA to found his own company, Ad Astra Rocket Company, specifically to continue the development of VASIMA. With a mix of private investment and partnerships, his team has continued to break records with their ground-based prototypes, steadily increasing the power levels and duration of their test fires. VASIMA embodies a critical lesson in technological maturation. A breakthrough idea is not enough. It requires patient, unwavering investment and a tolerance for long development cycles, something that often clashes with the short-term political and budgetary cycles of government agencies. The fact that private industry has picked up the torch offers a hopeful model for the future. suggesting that the most advanced ideas, even if they are too ambitious for their time, can find a way to survive, evolve, and perhaps one day propel the first humans to Mars on a gentle, continuous stream of starfire. While the Vasimer engine promised to revolutionize travel within our solar system, another team of visionaries was looking far beyond, to the cold, dark void between the stars. In the 1980s, a group of scientists at the Jet Propulsion Laboratory conceived a mission so audacious it would make the Voyager's grand tour look like a trip around the block. They called it the 1000 Astronomical Unit Mission, or TAU. Its objective was deceptively simple: to send an unmanned probe on a one-way journey to a distance of 1,000 O from the Sun. To grasp the sheer scale of this ambition, consider that 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. Pluto, the most distant known planet at the time, orbits at an average distance of just 40 O. The TAU probe was designed to travel 25 times farther than that, pushing into a region of space where the Sun would be little more than a particularly bright star in a sea of blackness, and where the gravitational influence of other stars begins to rival that of our own. This wasn't just a stunt to set a distance record, it was a mission of profound scientific discovery. The interstellar medium, the thin soup of gas and dust that exists between star systems, is almost entirely unknown to us because we are still trapped deep within the protective and distorting bubble of the Sun's solar wind, known as the heliosphere. The TAU probe would be the first human-made object to truly leave our solar system and enter this pristine galactic environment. Its instruments would have directly sampled this exotic matter, measured the strength of magnetic fields between the stars, and looked back at our solar system from the outside to precisely map the structure and boundaries of the heliosphere. Perhaps most excitingly, it would have used its unique vantage point, far from the interference of the Sun's light, to perform unparalleled astronomy. It could have precisely measured the distances to nearby stars using parallax with a baseline of 1,000 O, a method far more accurate than anything possible from Earth's orbit, and it could have trained its telescopes on the center of our galaxy or other cosmic phenomena with a clarity impossible to achieve from within our dusty galactic neighborhood. To achieve such an epic journey within a reasonable human lifetime, the mission was planned to last 50 years, required a propulsion system as radical as the destination. Chemical rockets were utterly useless for this task. The answer, once again, was nuclear. The TAU spacecraft was designed around a compact nuclear fission reactor that would power a highly efficient ion propulsion system, much like the one later envisioned for the Jupiter icy moon's orbiter. This nuclear electric engine would provide a gentle but continuous thrust for years on end, slowly accelerating the probe to a cruise velocity of 106 kilometers per second. At that incredible speed, it would cover the distance from Earth to the Moon in under an hour, and it would reach its namesake 1,000 goal within half a century, a timeline that would allow the scientists who designed it to potentially live to see the mission's culmination. The technological challenges, however, were as vast as the distances involved. The probe would need to be almost entirely autonomous, capable of navigating and managing its systems for decades without any possibility of real-time intervention from Earth, as communication delays would eventually stretch to over a week each way. It would require revolutionary advances in radiation-hardened computing, reliable communications over interstellar distances, and a power source that could operate flawlessly for longer than most satellites are designed to last. When the estimated price tag for developing and launching such a revolutionary vehicle was calculated, it ran into the billions of dollars. In the budgetary environment of the 1980s, and in competition with other high-profile planetary missions, TAU was deemed a bridge too far. It was a project whose scientific yield, while undeniably profound, was seen as too speculative and too long-term to justify its immense cost and complexity. The mission was officially shelved, its detailed reports filed away as a fascinating thought experiment. Yet the spirit of TAU refused to die. Its ambitious goals directly paved the way for later, more focused missions. The New Horizons probe, which gave us our first stunning close-ups of Pluto, carried on TAU's legacy of exploring the distant outer solar system. Even more significantly, TAU's core objective of reaching into interstellar space inspired the current Voyager interstellar mission, which is now actively returning data from beyond the heliosphere, and it fuels the ongoing scientific discussion about a future interstellar probe mission, a concept now being studied for a potential launch in the 2030s. The TAU mission stands as a magnificent monument to pure, unadulterated curiosity. It was a project born not from geopolitical competition or immediate practical benefit, but from a fundamental human desire to see what lies over the next hill, even when that hill is 1,000 times farther than anyone has ever gone before. It reminds us that our greatest explorations often begin not with a roar, but with a quiet, persistent question asked by those who dare to look beyond all known horizons. Imagine for a moment a future where the national flags planted on the lunar surface are not symbols of competition, but are woven together into a single, unified banner of human achievement. This was the powerful vision that emerged in the wake of the Cold War, a concept that seemed to finally be within our grasp: the International Lunar Base. As the 1990s dawned, the geopolitical landscape had shifted dramatically. The Soviet Union had dissolved, and the space race's fierce bilateral rivalry gave way to a new spirit of cooperation, perfectly embodied by the ongoing and complex construction of the International Space Station. It seemed only logical that humanity's next great step would be taken together. Scientists and diplomats alike began drawing up plans for a permanent outpost on the Moon, a truly global village where astronauts from every corner of the Earth could live and work side by side, using the Moon as a proving ground for the technologies needed to eventually reach Mars. The blueprints for this collaborative base were incredibly detailed and visionary. They envisioned modular habitats not unlike those on the ISS, but designed for the unique challenges of the lunar environment. These structures would be buried under layers of regolith for protection from radiation and micrometeorites, powered by a combination of solar arrays and small nuclear reactors. The plans called for international specialized contributions, perhaps a European life support module, a Japanese robotic rover garage, a Russian-built power unit, and an American-built core habitat. The scientific potential was staggering. An international base would allow for a continuous human presence, enabling long-term research into lunar geology, astronomy from the airless Moon's pristine surface, and the development of techniques for extracting water ice from permanently shadowed craters to create breathable air and rocket fuel. It was a vision of the Moon not as a territory to be claimed, but as a common resource for all humankind, a shared laboratory just 3 days from home. Yet, this beautiful vision of international harmony quickly collided with the enduring realities of earthly politics and economics. The primary obstacle was not a lack of will, but a misalignment of priorities and pocketbooks. The 1990s and 2000s were a period of relative peace, but also of shifting national interests and tightening budgets. The immense cost of building and maintaining the International Space Station consumed the majority of NASA and its partners' human spaceflight budgets. A lunar base, even a shared one, was seen as a bridge too far, an expense that few individual nations were willing to champion, and a project too complex to coordinate among a dozen different space agencies, each with its own political masters and bureaucratic hurdles. Furthermore, while the Cold War was over, underlying geopolitical tensions never fully disappeared, creating a persistent undercurrent of mistrust that made the kind of deep, seamless technological and financial integration required for a shared base incredibly difficult to negotiate. The dream was not abandoned, but it was indefinitely deferred, pushed to the back burner for nearly 2 decades. It took the rise of new global players in space, particularly China, and a renewed American commitment to return to the moon with the Artemis program, to finally breathe new life into the concept. The Artemis Accords, a set of international agreements, are the direct descendant of those 1990s dreams, attempting to create a framework for peaceful cooperation and to establish rules of the road for operating on the moon. But even now, the challenge remains immense, aligning the goals, timelines, and budgets of over 30 signatory nations is a diplomatic and logistical puzzle of epic proportions. The story of the International Lunar Base is a powerful lesson that in space exploration, the most advanced technology is not hardware or software, but the delicate and complex art of collaboration itself. It demonstrates that our greatest obstacles to becoming an interplanetary species may not be the voids of space, but the divisions we carry with us from Earth, and that the journey to other worlds first requires us to build bridges of understanding right here at home. While the world watched American astronauts drive across the moon, the Soviet Union was pursuing a completely different, and in many ways more technologically daring, path to exploration. Their champions were not astronauts but robots. The Lunokhod program, which means moonwalker, was a stunning achievement in remote-controlled robotics. Lunokhod 1 in 1970 became the first ever remote-controlled rover to land on another world, trundling across the lunar surface for 10 months. Its successor, Lunokhod 2, was even more capable, traveling an incredible 24 miles and sending back over 80,000 television images. These weren't simple machines, they were mobile laboratories the size of a small car, equipped with cameras, soil analyzers, and even a laser reflector that is still used for experiments today. They were a testament to Soviet engineering ingenuity, proving that complex scientific exploration could be conducted without ever risking a human life. By the mid-1970s, the engineers were ready for their masterpiece. Lunokhod 3 was built, tested, and ready for its mission. It represented the cumulative knowledge gained from its predecessors, a rover that was more advanced, more reliable, and more capable in every way. It featured improved cameras for even sharper stereo imagery, more sophisticated scientific instruments for geological analysis, and enhanced mobility systems to tackle even tougher terrain. This wasn't just a backup vehicle, it was the next evolutionary step designed to conduct the most detailed survey of the lunar surface ever attempted by a robotic explorer. It sat in its clean room, a perfectly assembled and fully functional piece of cutting-edge technology, waiting for its date with destiny and a rocket ride to the moon. But that rocket never came. The launch window for Lunokhod 3 opened and closed not because of a technical fault, but because of a political and programmatic collapse. The repeated, catastrophic failures of the giant N-1 rocket had already shattered the Soviet Union's dreams of sending cosmonauts to the moon. Without a human landing program to support, the robotic lunar missions began to look like an expensive luxury. The political will to continue, along with the necessary funding, evaporated almost overnight. The leadership lost interest in the moon, shifting its focus to the new frontier of space stations in Earth orbit. Just like that, the Lunokhod program was cancelled. The completed rover, a masterpiece of engineering that was literally ready to be packed into a rocket and change our understanding of the moon, was instead packed up and sent to a storage warehouse. It now sits on display in a Russian museum, a silent and pristine monument to a mission that was technologically ready but politically abandoned. The story of Lunokhod 3 is a uniquely poignant end to our journey through these unrealized projects because it embodies a final, crucial lesson. We have seen ideas that were too technologically audacious for their time, like the Orion nuclear pulse drive. We have seen concepts that were crushed by shifting political winds, like the Soviet Timke Mars mission. But Lunokhod 3 represents something even more frustrating, the project that was completely ready. The technology was not a dream, it was a reality sitting on the floor. Its failure to launch reminds us that innovation, even when perfectly executed, is never enough on its own. It requires a sustaining ecosystem of political support, consistent funding, and clear strategic vision. A perfect machine is powerless without a society committed to sending it on its journey. It is a sobering coda to our list, a tangible symbol of how the grandest plans can be grounded not by a failure of engineering, but by a failure of will. What emerges from this tapestry of abandoned blueprints and half-built prototypes is not a story of failure, but a masterclass in the complex anatomy of ambition. These 30 projects, for all their dazzling diversity, were almost all felled by a remarkably consistent set of challenges, forces so powerful they can ground even the most brilliant ideas. The first and perhaps most common is the simple reality of technological overreach. Time and again, we saw visionaries like those behind Project Orion or the Bussard Ramjet designing with the physics of the future, using slide rules and drafting tables to sketch out technologies that would require materials and computing power decades away from invention. They were solving tomorrow's problems with yesterday's tools, creating a visionary gap between the blueprint and the workshop that could not be closed quickly or cheaply enough to satisfy their funders. This is the classic pain of being too advanced. The idea is perfect, but the world around it is not yet ready to provide the necessary foundation. Closely intertwined with this is the ever-present specter of budget constraints. Space exploration is, by its very nature, astronomically expensive. A project like the Sea Dragon rocket or the Jupiter Icy Moon's orbiter represented not just a line item in a budget, but a massive reallocation of national resources. These endeavors exist in a constant state of competition with terrestrial priorities, social programs, military spending, infrastructure, and in that competition, a mission to Saturn or a base on the Moon can quickly be deemed a luxury the nation cannot afford. This is especially true when the political winds shift, which leads us to the third great killer, political volatility. The lifeline of any major space project is sustained political will across multiple election cycles and administrations. The cancellation of the Constellation program, despite significant investment, is a prime example of how a change in leadership can instantly redefine national priorities, leaving billion-dollar projects stranded without a champion. These projects are not just scientific ventures, they are political entities, and their survival depends on a fragile consensus that can vanish overnight. Finally, we cannot overlook the powerful role of societal fears and public perception. Even if the engineers solve all the technical problems and the politicians secure the funding, a project can still be doomed if it frightens the public. The notion of detonating nuclear bombs in space for propulsion, as in Project Orion, created an understandable and insurmountable ethical and environmental backlash. The public's visceral fear of launching nuclear material aboard the JIMO probe, however remote the actual risk, created a political firestorm that ultimately sealed its fate. In a democracy, the court of public opinion holds a veto power, and no amount of engineering brilliance can overcome a deep-seated public unease. Yet, for all these seemingly insurmountable obstacles, To view these stories as simple tragedies is to miss their true significance. Each one of these failures served as a crucial stepping stone. The advanced composites that failed on the X-33 taught SpaceX what not to do, saving them years of trial and error. The political and technical lessons learned from the Space Shuttle program are directly informing the safer, more sustainable architecture of the Artemis program. These unrealized dreams were not dead ends. They were the necessary, expensive, and often painful research and development phase for the successes we are only now beginning to enjoy. They are the invaluable negative data points without which true progress is impossible, proving that in the long arc of innovation, there is no such thing as a true waste of ambition. What we have explored together is far more than a simple catalogue of abandoned dreams. These 30 unrealized projects form a secret history of space exploration, a sprawling archive of what might have been that reveals just as much about our potential as it does about our limitations. They are not failures. A failure implies an attempt that fell short. These were ideas that, for a complex web of reasons, never got their full chance to fly. They are testaments to the breathtaking power of human creativity and the stubborn perseverance of the engineers, physicists, and visionaries who refused to be bound by the conventional wisdom of their era. Each one, from the atomic fire of Orion to the silent, waiting readiness of Lunar 3, offers a unique lesson etched into its blueprints. They teach us about the sobering realities of politics and budgets, the ethical dilemmas that accompany immense power, and the sheer, daunting challenge of pushing materials science to its absolute breaking point. Now, as we stand on the precipice of a new space age, these forgotten chapters feel more relevant than ever. We are witnessing a profound shift, a democratization of space driven by private companies like SpaceX and Blue Origin, and bolstered by new forms of international collaboration through agreements like the Artemis Accords. The lessons from these past endeavors are the foundational pillars of this new era. The cost-saving philosophy of the Sea Dragon rocket echoes in the reusable launch systems landing on drone ships today. The ambition of Mars Direct lives on in the plans for in-situ resource utilization on the Red Planet. The painful materials science lessons from the X-33 are the very reason newer rockets use more iterative, proven approaches. We are not starting from scratch. We are building upon the accumulated, hard-won knowledge of these ghost programs, finally applying the technologies and the political will that simply didn't exist decades ago. This is our charge then, as we look to the future, to dream with the same audacious scale as those 20th century pioneers, but to do so with the hard-earned wisdom their projects provided. Let us carry their spirit of innovation forward, not by blindly repeating their plans, but by learning from both their brilliance and their setbacks. Let us ensure that the next generation of space projects, the orbital hotels, the Martian cities, the probes to the stars, transcends the limits of its time, not just through technological superiority, but through sustainable funding, international cooperation, and a deep public engagement that turns fear into fascination. The past shows us that the only true limit is the one we place on our own imagination. Thank you for joining this incredible journey through the archives of ambition. These stories of what might have been are the very fuel for what will be. Let us know which of these projects you find most inspiring in the comments below, and be sure to subscribe for more deep dives into the technology that is